photograph of a city with a cloud icon superimposed over it. Figure 12. One cloud-native development and optimization is critical to delivering software applications securely, more rapidly, and continuously. Credit. Modification of Cloud by James Cridland/Flickr, CC by 20. Chapter Outline 12.1 Introduction to Cloud-Native Applications 12.2 Cloud-Based and Cloud-Native Applications Deployment Technologies 12.3 Example PaaS and FaaS deployments of cloud-native applications. Organizations are facing more pressure today to retain customers who depend on updated or new business capabilities. This requires organizations to deliver software applications securely, more rapidly, and continuously. For organizations to adapt existing applications or build new applications using cloud-native application development, they must abide by a different set of architectural constraints to leverage cloud infrastructure in comparison to traditional on-premises infrastructure. The focus should be on how to optimize these applications to leverage the capabilities that cloud platforms offer. There are 4 key principles of cloud-native development that help with designing applications for the cloud. First, applications should adopt a microservices architecture by breaking down the software into small components or services. Second, containerization must be applied to package microservices and isolate them for development and deployment. This not only speeds up development, but also makes it easier to quickly move isolated containers from one deployment environment to another. Containerization platforms such as Docker, an open-source platform used to deploy and run containerized applications, and container orchestration systems such as Kubernetes are instrumental in achieving this. Third, microservices are also more easily managed through continuous integration and continuous delivery. This makes it easier to automate the development and scale the deployment of highly resilient, manageable, and observable cloud-native applications. Fourth, DevOps facilitates the collaborative development of cloud-native applications using continuous delivery practices and results in shorter application development and deployment life cycles. DevOps allows development teams to adapt to changing user requirements more quickly while promoting business agility. By adopting these 4 key principles, organizations can speed up the process of cloud-native development and deployment. Cloud-native applications are critical to facilitate the creation of modern software solutions that interface with next-generation, secure super society, intelligent autonomous solutions, e.g. advanced robotics, autonomous cars and drones, or other autonomous systems. Organizations in many industries rely on the use of cloud-native applications to conduct business daily. Learning objectives. By the end of this section, you will be able to analyze the differences between monolithic and microservices architectures. Understand the architecture of cloud-native applications. Learn the features of cloud-native applications. Relate to the benefits of cloud-native applications. Understand best practices and tools used to develop cloud-native applications. Apply the tools used in cloud-native application development. Envision the road ahead for cloud-native applications. Cloud computing makes it possible for organizations to offer solutions in the cloud and use cloud services to streamline development and deployment. As organizations look to the cloud to solve today's business problems, they may opt to create, deploy, and manage cloud-based or cloud-native applications. As noted earlier, cloud-native development relies on 4 key principles that help with designing applications for the cloud, as illustrated in Figure 12. 2. A diagram with icons displays the 4 key principles of cloud-native development. It includes descriptions of microservices architecture, containerization, continuous delivery, and DevOps. Figure 12. 2. The 4 key principles of cloud-native development are microservices, containerization, continuous delivery, and DevOps. Attribution. Copyright Rice University, OpenStax under CC by 4. 0 license. In a nutshell, a cloud-native application uses a microservices architecture that takes full advantage of the benefits of the cloud, such as scalability and on-demand services. Cloud-based applications are adaptations of legacy applications, or monoliths, migrated to a cloud provider. They are designed to leverage cloud platforms to facilitate the interoperation of local and cloud components. Although cloud-based applications do leverage cloud platforms to some degree, they are generally deployed as a single monolithic component, which makes them inflexible, as full-stack upgrades are likely necessary and require downtime. Different from cloud-based applications, Cloud-native applications leverage microservices architectures that structure applications as coordinated collections of small, independent services that are self-contained and are deployed in software containers managed by a container orchestrator. Both cloud-based and cloud-native applications can run on public, private, or hybrid cloud infrastructures. A hybrid cloud combines private, public clouds and bare metal or virtual environments. What distinguishes cloud-native applications from cloud-based applications is the fact that they take full advantage of inherent characteristics of the cloud, such as resource pooling, on-demand self-managed services, automation, scalability, and rapid elasticity, to name a few. Monolithic versus microservices architecture. A monolithic architecture consists of software units that are united through a single code base. In a monolithic architecture, all the different components of the application, including the user interface, business logic, and data access layer, are tightly integrated and deployed as a single software unit. Mainframe applications or legacy e-commerce websites were based on monolithic architectures. A microservice is a self-contained software unit that typically implements a single business capability. Because microservices are independent and loosely coupled, changes to an individual microservice can be deployed separately and do not require updating the entire application. This in turn streamlines the application development and minimizes downtime. Monolithic architectures typically consist of a user interface, business logic, and data access layers that are tightly coupled and generally dependent on one another to operate properly. An application that conforms to a monolithic architecture, also called a monolith, implements all the business capabilities together, and data is shared across all these capabilities. Monoliths are typically easier to develop and deploy, but they may become difficult to manage and scale over time. The basic difference between a traditional monolithic architecture and a microservices architecture is illustrated in Figure 12. 3. A diagram shows the difference between monolithic architecture and microservices architecture. Figure 12. 3 monolithic architectures consist of highly dependent components and do not scale well compared to microservices architectures with self-contained components that are more easily scalable. Attribution, copyright Rice University, OpenStax, under CC by 40 license. As an example of a monolith, consider an application that provides a catalog of products that can be ordered online. An application designed using a monolith architecture is shown in Figure 12. 4. The application includes a user interface. The business logic layer includes various components such as an inventory system for the product catalog, a basket service to order products, a payment system to purchase the products, and a reporting system that generates reports on sales and customer interests. A component is a software unit that encapsulates a set of related functions and data through a well-defined interface and specified dependencies. A single database is typically used as part of the data access layer for the entire application. A diagram displays the following flow: user interface, business logic, inventory system, basket service, payment system, shipping service, reporting system, data access layer. Figure 12. 4. An application is designed using a monolithic architecture. Attribution, copyright Rice University, OpenStax, under CC by 40 license. These are highly dependent software components that use shared libraries. Any changes to one component require understanding what other components need from these shared libraries. Such changes can cause dependencies between components to break over time. The various components are also programming language and framework dependent. New components need to be implemented in the same programming language or use the same framework as the existing components. Other challenges with monoliths are managing growth and ensuring scalability. Over time, as new functionality is added to meet the needs of end users, the monolith grows and becomes more difficult to manage. Deploying the monolith then becomes challenging as it requires more effort to stabilize it and get it to run smoothly. Scaling a monolith also becomes more difficult over time. For example, during a holiday season with a rapid increase in sales, the payment system component may require additional capabilities to support a sudden increase in transactions. To add the necessary capabilities to just the payment system component, the entire monolith application needs to be duplicated. The problem with this is that deploying a second instance of the entire application and making it available to end users may take a lot of time. Before this gets done, the holiday season may have ended already, and the version of the application that was available was only able to support a limited number of transactions. The second instance of the application is useless at this point despite the effort it took to deploy it. A scaled version of the monolith application is shown in Figure 12. 5. A diagram shows the following flow. Load balancer user interface business logic, inventory system, basket service, payment system, shipping service, reporting system, data access layer. Figure 12. 5. An application that was designed to use a monolithic architecture is scaled to handle an increase in use. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0. License. In contrast, microservices architectures consist of small, loosely coupled services that run independently and connect via network. Applications that conform to a microservices architecture include a collection of modular components that run independently and provide a well-defined API to facilitate communication with other services. Instead of using a shared database across all business capabilities, each microservice that implements a single business capability contains its own data store, the type of which depends on the type of data needed. If the sample monolith application discussed earlier is implemented using a microservices architecture, each one of its components, i.e., the inventory system, basket service, payment system, and reporting system, becomes an individual microservice. These microservices each run in separate containers and communicate via APIs. An application designed using a microservices architecture is shown in Figure 12. 6. A diagram an application designed using a microservices architecture. It includes user interface, API gateway, inventory system, basket service, payment system, shipping service, reporting system, data store. Figure 12. 6. An application designed using a microservices architecture. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0. License. Components in a microservices architecture are independent of each other. Individual microservices can be changed without affecting the other microservices. If a microservice fails, the rest of the application is not affected. Microservices are also programming language and framework independent. New microservices can use different programming languages or frameworks. For example, a team responsible for the inventory system can use a programming language or framework that is different from the ones used to implement the payment system. It is also easier to grow or scale a microservices-based architecture. Additional functionality can be added to individual microservices independently from the other microservices. This allows teams to iterate faster to bring value to end users. Microservices can also scale independently, as shown in Figure 12. 7. During a holiday season with a rapid increase in sales, additional capabilities can be added to the payment system microservice quickly without affecting the other microservices. These additional capabilities can be scaled down as needed when sales decline after the holiday season ends. A diagram showing an application that was designed to use a microservices architecture is scaled to handle an increase in use. It includes user interface, API gateway, inventory system, basket service, load balancer, shipping service, payment system, data store. Figure 12. 7. An application that was designed to use a microservices architecture is scaled to handle an increase in use. Attribution, Copyright Rice University, OpenStax, under CC by 40 license. In summary, a monolith bundles all the capabilities together in a highly dependent way and requires them to use the same programming language and framework. Monoliths are more difficult to grow and scale because they require that the entire application be deployed as a second instance. In contrast, a microservices-centric application places individual capabilities in separate microservices that are deployed via containers and communicate via APIs. Individual capabilities are programming language and framework independent. They are easier to grow and scale independently, linked to learning. The article Microservices discusses the characteristics of a microservices architecture in contrast to a monolith architecture. Components versus services. Building applications using components is a desirable approach. In the case of monoliths, this is typically achieved by using libraries as components and compiling or linking them into a single program or process that accesses them using in-process function calls. In contrast, services in a microservices-centric application are out-of-process components that communicate with each other using a web service request or a remote procedure call. Figure 12. 8 illustrates how components are accessed in a monolithic architecture as compared to a microservices architecture. Two diagrams are shown. One shows the components in a monolith architecture, and another shows components in a microservices architecture. Figure 12, 8 components in a monolith architecture are accessed differently compared to components in a microservices architecture. Attribution, copyright Rice University, OpenStax, under CC by 4. 0 license. As noted earlier, services used by microservices-centric applications are independently deployable so that changes to any service do not affect other services. This assumes services are well encapsulated and designed with minimally cohesive service boundaries. The use of web services calls and RPC makes this easier to achieve. A web service is a unit of software that is available as a resource over the internet. A remote procedure call, RPC, is a request-response protocol used by a program to access services from other programs over a network. However, there are downsides to this approach. RPCs are more expensive than in-process calls, and thus remote APIs need to be coarser-grained, i.e., coarse-grained APIs expose more methods in their interfaces as opposed to fine-grained APIs. One challenge to using services is changing the allocation of responsibilities between components. This can be challenging especially if the service consists of multiple processes deployed together, such as an application process and a data store process that are only used by that service. Another challenge is that it may be difficult to get the components' service boundaries right. In other words, the difficulty is to fit software into a component that can be used as a service. Services use APIs, thus any changes to the API must be coordinated with other components. API changes must be backward compatible so components that do not use the latest updated version of the API can still function. Finally, testing is also more complicated. SOAV's microservices. The microservices architecture is not the first architectural style to make use of self-contained components and implement individual business capabilities. The service-oriented architectural style, a well-established style of software design, commands the same approach. A service-oriented architecture, SOA, requires that conforming applications be structured as discrete, reusable, and interoperable services that communicate through an enterprise service bus, ESB, via message protocols such as SOAP1 Active MQ2 or Apache Thrift. An enterprise service bus, ESB, implements a bus-like communication system between interacting service providers and service consumers. The services, ESB, and messaging protocols collectively make up an SOA application. In Figure 12.9, the architecture shown on the left illustrates a typical SOA compared to the typical microservices architecture illustrated on the right. As is the case for services in a microservices architecture, SOA services can be updated independently. However, the ESB represents a single point of failure for the entire system. Two diagrams are shown. One shows SOA architecture, the other shows microservices architecture, Figure 12.9. In an SOA, services communicate via an ESB compared to a microservices architecture, where services typically communicate via REST protocols. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Different from services in an SOA, microservices usually communicate with each other statelessly using lightweight REST protocols implemented via HTTP. Furthermore, microservices can be implemented using different programming languages and frameworks because they can communicate through programming language-agnostic APIs. Advancements in containerization technologies make it possible to deploy, upgrade, scale, and restart microservices independently, better controlling their life cycles. In case a microservice fails, the rest of the application is unaffected. Thus, applications using microservices can be more fault-tolerant because they do not rely on a single ESB, as is the case for SOA applications. Concepts in practice. Microservices architecture and cloud-native applications. As discussed in Chapter 9 Software Engineering and Chapter 10 Enterprise and Solution Architectures Management, architectural styles, architectural patterns, and design patterns are typically used to enforce the quality attributes of software solutions. The microservices architectural style is used to break monolithic applications into smaller services based on business capabilities. It is partially based on the SOA style, but does not rely on an enterprise service bus to enable communication between services. One example of a microservices design pattern is the backend for frontend BFF microservice design pattern. For this design pattern involves creating dedicated backend services tailored to the specific needs of front-end clients. The goal of this pattern is to ensure an efficient and streamlined interaction between the front-end and back-end components. As an example of how to use this pattern, consider an e-commerce platform like the online products catalog sample described above. The e-commerce platform may serve both web and mobile client applications. Implementing the BFF pattern means creating dedicated back-end components that serve each client application. Because the user interactions between these two client applications are different, the APIs between these clients and the dedicated back-end services can be optimized to best suit those client types. In addition to optimizing the API gateway, the microservices architecture utilized also efficiently allocates resources to each service that a cloud-native application uses, making the application flexible and adaptable to a cloud architecture. Containers are an architectural pattern that is used to deploy microservices on any platform that operates a container engine runtime. Combining microservices and containers with another architectural pattern, referred to as container orchestration, makes it possible to scale, manage, and automate the deployment of containerized applications based on microservices. This is an example of how a combination of architectural styles and related patterns can drastically improve the quality of enterprise applications. However, as noted earlier, there are challenges associated with the use of microservices and other architectural styles that also must be considered when designing an enterprise solution. Microservices challenges. Microservices enhance a development team's ability to leverage distributed development. Development time can be reduced as microservices can be developed concurrently. However, there are known challenges to shifting to a microservices architecture. In addition to complexity and efficiency being two major challenges of a microservices-based architecture, the following 8 challenge categories have been identified. Building microservices. Some microservices may need to access other microservices to provide certain application functionality. This causes dependencies between microservices. Time must be spent identifying these dependencies. Added dependencies between microservices can result in completing one build that triggers several subsequent builds. Another type of dependency is data sharing, where one microservice may need access to data managed by another microservice. Some concerns with data sharing include scaling. As microservices are added, to provide data consistency and redundancy, a microservice that requires a schema change in a database must be shared with other microservices. These concerns should also be taken into consideration when addressing dependencies. Microservices connectivity. Microservices-based applications consist of several microservices that need to communicate with each other. Microservices run in containerized environments where the number of microservices instances and locations change dynamically. Service discovery can be used to locate each microservice instance. Without service discovery, a microservices-based application can be difficult to maintain. Versioning of microservices. A microservice might be updated to satisfy new requirements or address some design issues. Other microservices that depend on an older version of the updated microservice could fail. Dependencies between microservices when updating a microservice can lead to breaking backward compatibility. One way to address this is to build in conditional logic that either appends the version number or tracks versioning, which can become difficult to manage. Alternatively, multiple live versions can be provided for different clients, but they can also become difficult to manage. Testing microservices. Testing microservices can become more challenging, particularly with integration testing and end-to-end testing. A single transaction carried out in an application can span across multiple microservices. A failure in one microservice can lead to failures in other microservices. In addition, failures can occur in the microservice itself, in its container, or in the network interconnecting the microservices, making it more challenging to design integration tests. For these reasons, an integration test plan should factor in interdependencies between microservices. Linked to learning. Various tools and/or frameworks can help automate testing in a microservices testing, such as Selenium automation testing. Logging microservices. Microservices are distributed systems, and therefore traditional logging is ineffective when determining which microservices failed. As more microservices are added, the complexity of logging microservices activities grows exponentially and becomes more difficult to manage. In particular, logging aggregation is needed to track errors that might span across several microservices, as shown in Figure 12. 10. A diagram shows a microservices architecture configured to use log aggregation and distributed tracing. Figure 12.10. A microservices architecture is configured to use log aggregation and distributed tracing, which are typically used in a microservices-based distributed system. Log aggregation refers to storing various levels of warning and errors for a combined set of microservices. Distributed tracing helps interrelate information logged by multiple services so it can be followed as a single thread. Attribution, copyright Rice University, OpenStax, under CC by 40 license. Debugging microservices. Remote debugging through a local integrated development environment will not work across several microservices. An IDE provides developers access to resources, e.g. source code editor, build automation tools, debuggers, to design, develop, debug, and test programs. Debugging a microservices-based application is challenging because errors are not propagated in a useful manner. In addition, logging formats can also differ across microservices. Debugging requires tracing through various error messages and status codes across the network, which is inefficient and makes it difficult to acquire the required information to debug the errors. Currently, there is no easy solution to debugging such applications effectively. However, tools e.g. Helios 5 Rookout, 6 Lightrun, 7 do exist today to address this problem. Deployment of microservices. A monolithic application's deployment may seem less complex because it is limited to a single deployment unit. In contrast, a microservices-based application is more complex to deploy because the interconnections between the microservices are more visible. In addition, there are more deployable units, and the dependencies between them require more complex configurations. This increase in the number of deployable units imposes an order in which microservices need to be deployed. It also requires more investment in automation to practically manage them and help ensure that the whole microservices-based application is resilient and limits the risks of failovers. Monitoring microservices. Because of the interdependencies between microservices, any downtime of a microservice resulting from updates or failures can cause cascading failures to other microservices. Monitoring a microservices-based application is challenging because it requires knowledge of the performance and availability of API calls for all the microservices in the application. In addition to monitoring the containers hosting the microservices, it is crucial to have a centralized view of the entire microservices-based application. This holistic view helps pinpoint any potential issues and ensures effective problem identification. Cloud-native application architecture. A cloud-native application takes advantage of cloud computing frameworks to implement a collection of loosely coupled microservices in the cloud. The cloud-native application architecture makes it possible to efficiently allocate resources to individual microservices that the cloud-native application uses. An example of a cloud-native application architecture is illustrated in Figure 12.11. A diagram shows a cloud-native application architecture. It includes user interface, API gateway, inventory system, basket service, payment system, shipping service, reporting system, data store, cloud-native application and runtime environment, scheduling and orchestration, and cloud infrastructure. Figure 12.11. A cloud-native application architecture includes the cloud-native application and the cloud computing platform it leverages. Attribution, copyright Rice University, OpenStax, under CC by 40 license. The cloud infrastructure, shown in Figure 12.11, is provided by a cloud computing platform. The cloud computing platform also provides a scheduling and orchestration service to manage the containers that the cloud-native application microservices are deployed in. Microservices used in a cloud-native application typically run in different locations within a cloud platform, which enables the application to scale out horizontally. Therefore, cloud-native applications must be designed with redundancy in mind. This allows the application to withstand equipment failures. Finally, the cloud-native application and runtime environment is where the cloud-native application operates. A cloud-native architecture leverages a commoditized microservices architecture. In this architecture, business capabilities are implemented as cloud-managed microservices, which makes the cloud-native application more reliable and scalable. Cloud-native applications should be designed to include standardized logging and support events that can be associated with a standard logging catalog. Scaling and managing multiple microservices require core services such as load balancing, service discovery, and routing, which are all managed by the scheduling and orchestration layer. In summary, designing cloud-native applications to leverage the services of a cloud computing framework makes it possible to add and support new business capabilities more quickly. Sample web-native architecture. Figure 12 illustrates a sample web-based, cloud-native, web-native architecture. This cloud-native application consists of several microservices that are deployed and managed on the cloud. Each microservice is self-contained as well as programming language and framework independent. Microservices are containerized and managed by a container orchestrator. Each microservice contains its data store that best suits its data needs. Some of these data stores are relational databases, whereas others are NoSQL databases. A diagram shows a web-native application. Figure 12. A web-native application leverages features of modern cloud platforms. 8. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0. License. One of the microservices stores its state in a distributed Redis cache. An API gateway is used to route traffic between client apps and microservices. Most important, this cloud-native application takes full advantage of the scalability and resiliency features of modern cloud platforms. Industry Spotlight. Cloud-native application in industry. Cloud-native applications are broadly used in the industry today. In particular, Netflix, Uber, and WeChat expose cloud-native systems that consist of many independent services. Can you elaborate on the specific characteristics of these systems and explain why cloud-native is more suitable for the types of solutions provided by these companies? As an example, Netflix published the article, Completing the Netflix Cloud Migration, 9 discussing the benefits of this migration. A case study 10 was also published discussing Netflix's adoption of cloud-native computing environments for their services. Features of cloud-native applications. As mentioned previously, cloud-native applications, in contrast to cloud-based applications, leverage inherent characteristics of the cloud such as resource pooling, on-demand self-services, automation, scalability, and rapid elasticity. Below is a list of the key capabilities of cloud-native applications that make this possible. Microservices-based applications. As noted earlier, microservices are based on a software architectural pattern where every functionality of a corresponding monolithic application is placed into its own microservice because it implements a separate business capability. These microservices are deployed and run in containers that communicate over application APIs, event streaming, and message brokers. Scheduling and orchestration tools manage these containers as they help coordinate and schedule the containers used to implement application services running on computing resources. Microservices development teams can rapidly add new capabilities whenever a business needs change. Microservices can also be scaled when a single capability faces too much load, independently of other microservices. This reduces the time and cost associated with having to scale another instance of the entire application. Typically, scaling is achieved by containerizing microservices and managing the containers using a container management framework, e.g. provided by a cloud platform. Another alternative is to leverage function as a service, e.g. AWS Lambdas or Google/Microsoft functions, as part of microservices and rely on cloud platform, to manage scalability. Microservices are also distributed and loosely coupled, making them easier to iterate through. Because microservices are independent and just communicate over APIs, teams can commit code for microservices through a DevOps pipeline. Once tested, the microservices can be automatically deployed, making it easier for teams to iterate as fast as they need to bring value to end users. Additionally, these iterations are minimal, and if there is any instance where a microservice fails, the rest of the application is still functional, making updates less risky. Best suited languages and frameworks for microservices. The programming language and framework are chosen based on what is best suited for the functionality the microservice provides. Cloud-native applications are polyglots, meaning microservices are language and framework independent, making it possible to choose different technology stacks and frameworks for different microservices of a single cloud-native application. Container-based framework. A container is a standardized unit of software that logically isolates an application, enabling it to run independently of physical resources. The packaging of a standardized unit of software that isolates an application, enabling it to run independently of physical resources, is containerization. Containers provide consistent, complete, and portable environments for running applications anywhere, including all the system files and dependencies needed to run applications. Containerization facilitates the creation of cloud-native applications and maximizes the benefits of containers. Containers keep microservices from interfering with one another. They keep applications from consuming all the host's shared resources. They also enable multiple instances of the same microservice. Containers boost DevOps efficiency and effectiveness through streamlined builds, testing, and deployments. They also provide consistent production environments that are isolated from other applications and processes. Because containers can run consistently anywhere, they facilitate hybrid and multi-cloud computing environments. Containers are lightweight because they are isolated from the operating system layer of a computer system. This makes them efficient and light on resources. Containers are portable because containers include all required dependencies and configurations. Thus they, and the code contained within them, can be moved between different environments. Figure 12.13 shows how containers in production can run on any computing resource that has a containerization platform. Containers are scalable due to their small size, making it easy to rapidly start up, scale, or shut down containers depending on use. Containers can be cost-effective because they require fewer resources and are easier to scale. A diagram shows the following flow: Cloud Native Application Developer, Client, Application Image Definition, create images, container platform, arrows to all of the following: cloud, virtual machines, on-premise servers, image repository. Figure 12.13 An image is built to deploy an application into containers that run on different computing resources. Attribution: Copyright Rice University, OpenStax, under CC by 4. 0 license. Containers are instances of a container image. A container image represents a binary state that is built by layering an application and its dependencies on top of the required layer of binaries and libraries of the operating system, which establishes a parent-child relationship between image layers. Figure 12.14 shows the process for building an image. For example, at the root of the parent-child tree is a layer that provides a formatted file system. On top of this layer is a base image that might contain Ubuntu, Debian, CentOS, or some other operating system. This base image can then be a parent of some other image, such as an image that adds Python. Finally, another image on top of the Python image may contain the application that was implemented in Python, such as a Django web application. Django is an open-source web application framework, which is a software framework that facilitates the development, maintenance, and scaling of web applications. In effect, these layers of images are arranged in an image hierarchy where each layer creates a snapshot. A diagram shows the following flow: Cloud Native Application Developer, Client, Application Image Definition, Writable Container, Add Django Image, Add Python Image, Ubuntu Base Image, FS Kernel, Create Images, Container Platform, arrows to all of the following: cloud, virtual machines, on-premise servers, image repository. Figure 12.14 Images are built as layers of an application, its dependencies, and other required layers. Attribution: Copyright Rice University, OpenStax, under CC by 4. 0 license. An advantage of this hierarchical structure is that it makes it possible to share images at different levels of the hierarchy. If you want to run the Django web application, you pull the entire hierarchy of the built image. However, other layers of the hierarchy can be shared with other things, e.g., the Python layer, reducing the need to shift entire application stacks. The built container image is an independent and self-contained artifact that can be deployed in any environment that has a container runtime environment, e.g., Docker installed. The Open Container Initiative is a community trying to govern and address uniformity and standardization of the container runtimes and images. This is an important initiative for containers to be able to build once and run anywhere. API-based framework. Microservices that rely on each other communicate using well-defined APIs. These APIs help configure the infrastructure layers to facilitate resource sharing across them. APIs connect microservices and containers while providing simplified maintenance and security. They enable microservices to communicate between otherwise loosely coupled services without sharing the same technology stacks, libraries, or frameworks. Cloud-native microservices use lightweight APIs that are based on protocols such as representational state transfer to expose their functionality. The architectural style for providing standards between resources so they can communicate with each other over the web is called representational state transfer, REST. Dynamically orchestrated framework. As already mentioned, the scheduling and orchestration layer of a cloud computing framework manages the containers microservices are deployed in. As applications grow to span multiple containers deployed across multiple servers, operating them becomes more complicated. Container orchestration tools, e.g. Kubernetes, can help coordinate and schedule many containers. They can also help scale container instances to provide more computational power. For example, the orchestration tool, depicted as master in Figure 12. 15 deploys the microservices in containers, single instances, initially, of an application on a computing resource. A diagram shows a container orchestration. It includes microservices in containers, deploy scale, and network containers. Figure 12. 15 container orchestration is used to manage microservices in a cloud-native application. Attribution. Copyright Rice University, OpenStax, under CC BY 40 license. As the microservices consumption of the computing resources increases, additional resources are added, and the orchestration tool will start scheduling and scaling the microservices. An orchestration platform helps schedule the microservices and containers and optimizes the use of the computing resource. In contrast, a monolith application is not designed to leverage an orchestration platform and requires the use of load balancers. Other services, such as service discovery, also need to be performed manually. For example, if microservices need to communicate with one another, they cannot find the IP addresses of their respective containers and check if they are running. This is handled automatically by the orchestration platform, i.e., Microsoft AKS, Amazon AWS EKS, Google GKE. An orchestration platform typically runs workloads by placing corresponding containers into pods that run on nodes, i.e., a virtual or physical machine. Multiple nodes are typically grouped into clusters to ensure scalability. Pods are the smallest deployable units of computing. They group multiple containers, provide shared storage and network resources, and specify how to run the containers. The orchestration platform provides support when a pod that contains a running microservice container goes down. In that case, another pod is brought up rapidly and brings it within the purview of that service automatically. Figure 12:16 shows how microservice containers are scaled and managed in the case of failure. A diagram shows container orchestration. It includes microservices in containers, deploy scale, and network containers. Figure 12:16 container orchestration is used to auto-scale and perform health checking of microservices in a scaled cloud-native application. Attribution, Copyright Rice University, OpenStax, under CC BY 40 license. Agile DevOps and automation using CI/CD. DevOps is a methodology that combines agile software development and IT operations to deliver software faster and of higher quality. Because DevOps and cloud native focus on different aspects of the application development process, they complement each other in facilitating agility. DevOps focuses on the principles and practices used in development and operations. A goal of DevOps is to ensure that all team members are cross-functional, so they have a single mindset on improving customer experiences, responding faster to business needs, and ensuring that innovation is balanced with security and operational needs. Cloud Native, on the other hand, focuses on the application environment and how to scale and deliver software more efficiently. The use of a DevOps pipeline to migrate an application toward a microservices architecture achieves the goals of automation, discipline, and repeatability while reducing some of the challenges already identified. As a cloud-native application works its way through the DevOps pipeline, it also moves toward continuous delivery. Figure 12:17 shows continuous integration and continuous deployment, CI/CD, which is a set of DevOps operating principles that enable development teams to focus on rapid and frequent integrations of new code into the application and development, as well as fast and frequent delivery or deployment of new iterations of the application. It allows teams to deliver code changes more frequently and reliably. A DevOps team establishes a CI/CD pipeline, which is a series of steps needed for integration and delivery or deployment that includes the build process through which the application is compiled, built, packaged, and tested. The continuous integration part automates the application compile, build, package, and testing process, enabling it to run independent of physical resources, which allows for a more consistent integration process. This improves team communication and leads to better software quality. The continuous delivery part goes a step further and automates the deployment stage as well. During this phase, the application is deployed to selected infrastructure environments. Packages built during CI are deployed into multiple environments, e.g., development, staging. The application build undergoes integration and performance tests. Finally, the application is deployed into production and made available to end users. A diagram shows a DevOps pipeline. It shows user interface, API gateway inventory system, reporting system, payment system, shipping service, basket service, DevOps pipeline. Figure 12. 17. A DevOps pipeline is used for a cloud-native app as its microservices code updates move through it. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0. License. Elastic dynamic scale up-down. Cloud-native applications take advantage of the elasticity of the cloud by scaling microservices. Microservices that require additional resources can be scaled on demand to service an increased capacity. The microservice can also be scaled down when usage decreases. Resources that were allocated during the scale-up can be deallocated as they are no longer needed. A cloud-native application can thus adjust to the increased or decreased resources and scale as needed. Benefits of cloud-native applications. Cloud-native applications are designed and built to take advantage of the speed and efficiency of the cloud. Cloud-native applications are highly scalable, easy to update, and take advantage of cloud platforms, processes, and services to easily extend their capabilities. Some of the benefits of using cloud-native applications include the following: cost-effectiveness. Orchestration tools can help scale a cloud-native application by automating the allocation of resources to the microservices as needed without having to duplicate the entire application. This eliminates the overprovisioning of hardware and the need for load balancing. Containers can also be used to reduce the complexity of managing the many microservices that make up a cloud-native application, as well as maximize the number of microservices that run on a host, saving time, resources, and money. Scalability. Each microservice is logically isolated and can scale independently without downtime. Microservices can scale up or down by allocating more or fewer resources to in-demand services in response to a change in user traffic. If one microservice is changed to scale, the others are not affected. Independent scalability also makes it easier to deploy or update any part of the cloud-native application without affecting the entire application. Portability. Cloud-native applications are vendor-neutral because the containers microservices run in can be deployed anywhere, thereby avoiding vendor lock-in. Reliability and resiliency. If a failure occurs in one microservice, there is no effect on adjacent microservices because cloud-native applications use containers. Resiliency is provided at the core of the architecture. As with any software system, failure can also occur in distributed systems and hardware. Transient failures can also occur in networks. The ability of a system to recover from failures and continue to function is called resiliency. The goal of resiliency is to return the application to a fully functioning state following a failure, minimizing downtime and data loss. An application is resilient if it 1. Has high availability, which is the ability for an application to continue running in a healthy state without significant downtime, and 2. Supports disaster recovery, which is the ability of the application to recover from rare but major incidents, non-transient, wide-scale failures, such as service disruption that affects an entire region. Applications can be made resilient by increasing redundancy with multi-node clusters, multi-region deployments, and data replication. Other strategies for implementing resiliency include retries to handle transient network failures, adding more nodes to a cluster and load balance across them, throttling high-volume users, and applying circuit breakers to prevent an application from repeatedly trying an operation that is likely to fail. Testing for resiliency requires testing how the end-to-end workload performs under failure conditions that only occur intermittently. For example, injecting failures by crashing processes, including expired certificates, making dependent services unavailable, and so on. Resiliency tools and frameworks like Chaos Monkey can be used for such chaos testing. For example, Netflix uses Chaos Monkey for resiliency testing to simulate failures and address them. Ease of management. Cloud-native application updates and added features are automated as they move through a DevOps pipeline using CI/CD. This makes it easier for developers to track the microservices as they are being updated. Development teams can focus on managing specific microservices without worrying about how it will interact with other microservices. This architecture allows teams to be chosen to manage specific microservices based on the skill sets of their members. Visibility, because a microservices architecture isolates services, it makes it easier for teams to learn how the microservices function together and have a better understanding of the cloud-native application as a whole. Best practices for cloud-native application development. Best practices for designing cloud-native applications are based on the DevOps principle of operational excellence to ensure the timely delivery of quality software. A cloud-native architecture has no unique rules, and businesses will approach development differently based on the business problem they are solving and the software they are using. Adopting the DevOps principles to develop cloud-native applications, businesses gain three core advantages, such as higher quality software released more rapidly, faster responsiveness to customer needs, and improved working environment for development teams. All cloud-native application designs should consider how the application will be built, how performance is measured, and how teams foster continuous improvement of the application's performance, compliance through the application lifecycle at a faster pace, and higher quality. Here are the 5 essential best practices for cloud-native application design. Automation. A development team should automate as much of the cloud-native application development lifecycle as possible. Automation helps reduce human errors and increase team productivity. It also allows for the consistent provisioning of cloud application environments across multiple cloud vendors. With automation, infrastructure as code, ISC, is used as a DevOps practice that uses versioning and a declarative language to automate the provisioning of infrastructure resources such as compute services, networks, and storage. Monitoring. Teams should monitor the development environment, as well as how the application is being used. Monitoring ensures the cloud-native application performs without issues. Teams can also bolster the CI/CD pipeline with continuous monitoring of the application, logs, and supporting infrastructure. Continuous monitoring can also be used to identify productivity issues that may slow down the CI/CD pipeline. Documentation. Many teams build cloud-native applications with limited to no visibility into what other teams are doing. Teams with specific skills are likely to manage certain aspects of the cloud-native application because microservices are built with different programming languages and frameworks that team members specialize in. It is important to document the specifics of the microservices they manage, track changes, and monitor team contributions to the cloud-native application. Incremental releases. Changes made to the cloud-native application or the underlying architecture should be incremental and reversible. With ISC, developers can track changes in a source repository. Updates should be released as often as possible. Incremental releases reduce the possibility of errors and incompatibility issues. Designed for failure. Processes should be designed for the possibility of failures in a cloud environment. Implementing test frameworks to simulate failures can mitigate risks. They can also be used to learn from failures and to improve the overall functionality of the cloud-native application. Global issues in technology. Local and international implications of cloud applications. While cloud-native applications are used all over the world, specific internationalization, I-18N, and localization, L10N, requirements must be observed to facilitate the creation of applications that people can use. Because microservices are part of an application's backend, they typically return keywords that can be replaced via I-18N L10N system within the application front end. What is your opinion regarding whether this approach addresses all I-18N L10N requirements for cloud-native applications? Tools for cloud-native application development. Several tools are used for the cloud-native application development process. Together, they create a development stack. The following tools are typically found in a cloud-native development stack. Docker. Docker is an open-source platform that creates, deploys, and manages containers using a common operating system. It isolates resources, allowing multiple containers to use the same OS without contention. Docker has become the standard for container technology. An advantage containers offer is portability. Docker containers can be deployed anywhere, on any physical virtual machine, or on the cloud. Using Docker helps reduce the size of development and provides smaller footprints of operating systems in containers. Typically measured in megabytes, Docker containers use far fewer resources than virtual machines and start up almost immediately. Docker containers are lightweight, which makes them easily scalable. Figure 12. 18 illustrates an overview of the Docker process. A diagram with the following flow is shown. Application Dockerfile build writable container, add app image, Python runtime image, Ubuntu base image, FS kernel run container. Figure 12. 18. A Docker image is built from a Docker file to deploy an application that runs in a Docker container. Attribution, copyright Rice University, OpenStax, under CC by 4. 0. License. To deploy applications using Docker, the typical first step is to create a Docker file. The Docker file is a text document that contains instructions for building a Docker image. A Docker image may be based on another image with some additional customization. Docker images are a collection of immutable layers where each instruction in a Docker file creates a layer in the image. Once built, Docker images become immutable templates for creating Docker containers, which are running instances of those images containing everything needed for the application to run. Kubernetes. Kubernetes is an open-source orchestration platform used for automating deployment, scaling, and management of container-based workloads. An example of a Kubernetes platform is shown in Figure 12.19. A complex diagram showing a cloud-native application deployed in a Kubernetes environment is shown. Figure 12.19. A cloud-native application is deployed in a Kubernetes environment. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. The workload refers to an application being run on Kubernetes. The Kubernetes master node includes the control plane, which has several important components, including a service controller, node controller, endpoint controller, replication controller, and scheduler. These components are responsible for features such as load balancing by distributing network requests across containers efficiently, self-healing containers by regularly checking them for good health, and where failed containers are replaced or restarted automatically. Auto-scaling containers by adding or removing them in accordance with demand. Automated deployment to handle setting up and deploying containers to the cloud. Storage management to handle the storage needs of all the containers. And handling networking between containers. The Kubernetes master node comprises several components, including the Kubernetes API server, which plays a crucial role in managing container-based workloads. Additionally, the Kubernetes cluster consists of worker nodes, each containing a kubelet. Working in tandem with the master node, the kubelet handles tasks like scheduling and ensuring the smooth operation of applications deployed within the worker nodes. Kubernetes has evolved into the preferred platform for deploying cloud-native applications. In this ecosystem, the microservices of a cloud-native application interact over the network, deployed and scaled within a Kubernetes cluster. To deploy a cloud-native application in a Kubernetes environment, microservice containers, pulled from a registry, are deployed in pods. A pod is a small logical unit that runs a container within a worker node in the Kubernetes cluster. A cluster is a set of one or more nodes. Pods are a group of one or more containers with shared storage network resources and a specification for how the containers are run. Containers should only be scheduled together in a single pod if they are tightly coupled and need to share resources. Pods are ephemeral, meaning they are non-permanent resources. Kubernetes manages the pods rather than the containers directly. The API server on the Kubernetes master node communicates with the worker node to deploy the container in a pod and start it up. Replicas of pods can be increased to scale the containerized microservice within it. If a pod fails, a new one is created. Kubernetes manages these deployments for the length of the deployment until the pod is deleted. In other words, it ensures that all pods and replicas are running. Service discovery is another important service provided by the Kubernetes platform. As pods are added and replicated, an internal IP address is provided for the pod, making the container accessible. Pods are ephemeral, so IP addresses can change as new pods are created. Service registry and service discovery capabilities address this issue by creating Kubernetes services. A Kubernetes service is an abstraction which defines a logical set of pods and a policy by which to access them in a reliable way. Think it through. Are Docker and Kubernetes too broad? Given the fact that many tools are available for containerization and container orchestration, what justifies the broad acceptance of Docker and Kubernetes to handle these respective functions? Terraform. Terraform is an open-source ISC tool used to build, update, and version cloud and on-premises resources. Some use cases for Terraform include managing Kubernetes clusters and provisioning resources in the cloud, among many others. GitLab and GitHub CI/CD. GitLab is a cloud-based DevOps platform used to monitor, test, and deploy application code. GitLab includes a cloud-based Git repository, as well as several DevOps features such as CI/CD, security, and application development tools. The CI/CD tool can be used to automate testing, deployment, and monitoring applications. GitLab can also be used for security analysis, static analysis, and unit testing. GitHub is a cloud-based developer platform used for software development, collaboration, and security. GitHub also includes a cloud-based Git repository and several DevOps features similar to GitLab. Red Hat OpenShift. OpenShift is Red Hat's cloud application platform. It includes several containerization software products, including the OpenShift container platform that runs on the Red Hat Linux operating system and Kubernetes. OpenShift is a platform as a service (PaaS) that includes the Kubernetes platform, Docker container images, as well as features that are exclusive to the OpenShift platform. Such features include CI/CD pipeline definitions, container automation tools, Kubernetes command line interface, and security features. OpenShift provides a robust, multilanguage development environment, plus all the necessary software components to support applications. OpenShift is open source and free-to-download application that enables developers to quickly deploy web, mobile, and IoT applications. Tanzu. VMware's cloud application software Tanzu, formerly known as Cloud Foundry, is a modular application platform that provides a rich set of developer tools and a pre-paved path to production to build and deploy applications quickly and securely on any compliant public cloud or on-premises Kubernetes cluster. Tanzu provides a supply chain of operational and security outcomes for the development environment via configurations that are designed with operational and security principles, so that applications can be pushed into production quickly, run, and scaled safely and securely. Such principles include running code through a testing environment and ensuring the code runs properly, applying security scanning so that the application that goes into production is audited and compliant with security policies, and deploying the application to production environments that may include several cluster environments that can run and scale in production. Node. Node is an open-source, cross-platform, server-side JavaScript runtime environment that can be used to develop server-side tools and applications in JavaScript. Some examples of real-time applications include chats, news feeds, and other microservices. For example, Node can be used to create virtual servers and define the routes that connect microservices to external APIs such as operating system APIs, including HTTP and file system libraries, compared to browser-specific JavaScript APIs. Link to learning. This cloud-native trail map illustrates the use of various open-source tools to develop cloud-native applications. The future of cloud-native applications. Cloud-native applications have seen increased use in recent years and are predicted to be the future of software development. The Cloud Native Computing Foundation, 11, estimated there were at least 6.8 million cloud-native developers in 2021 compared to 6.5 million in 2020. They also estimated there were 5.6 million developers using Kubernetes in 2021, up 67% from a year ago. 12. Cloud-native applications solve some of cloud computing's inherent problems. The cloud-native approach is the new standard for enterprise architecture. It is a way of designing, building, and running applications in the cloud. It has been observed that companies that adopt a cloud-native approach can achieve higher levels of innovation, agility, and scalability. It also offers many benefits such as reducing IT overhead and management costs by providing a streamlined software delivery process and on-demand consumption of resources, reducing time to market and reducing the risk of deployments by enabling developers to rapidly build, test, and deploy new and updated services, ability to react faster in the market due to constant availability of resources, reduction in complexity, less coupling between the services in an application. Nevertheless, migrating to the cloud to improve operational efficiencies has a range of challenges. We also pointed out earlier some of the challenges faced in microservices architectures. Some of the challenges that were learned earlier include to use microservices requires changing the allocation of responsibility between components and determining the components. Service boundaries could be difficult, debugging, logging, and monitoring microservices also become challenging, to name a few. Technology in everyday life. Everyday life and microservices. There are myriads of web apps that people use every day that are based on microservices. For example, whether apps typically leverage web services that invoke microservices. More complex applications include e-commerce websites, as illustrated earlier. Can you provide additional illustrative scenarios that demonstrate how the use of microservices help people in everyday life? Your scenarios should not be limited to describing how microservices are used, but rather should describe situations where these architectures are applied in real-life contexts. Learning objectives. By the end of this section, you will be able to understand cloud deployment technology, relate to cloud deployment technology options, explain cloud deployment technology, use cases and implementation, select cloud deployment technologies, relate to the future of cloud deployment technologies. Various cloud technologies may be used to deploy cloud-based and cloud-native applications. These technologies differ in their implementation and use. While these technologies span storage, network, and compute services, the emphasis will be on compute options. There are many deployment options available, and there is no right or wrong choice. Only a subset of these options is applicable to the deployment of cloud-native applications. However, all options will be covered because enterprise solutions are typically hybrid solutions that may combine on-premises, cloud-based, and cloud-native components. Many organizations will need to implement more than one option. Accordingly, selecting the best option to support workloads while controlling complexity can be a daunting task. Introduction to cloud deployment technology. The delivery of computing services, such as databases, software, analytics, and storage over the internet, is called cloud computing. The cloud computing model is composed of three service models: infrastructure as a service (IaaS), platform as a service (PaaS), and software as a service (SaaS), and four deployment models: private cloud, community cloud, public cloud, and hybrid cloud. Figure 12.20 describes the relationship between cloud deployment models, service models, and cloud deployment technologies. A diagram shows the following flow. Cloud computing with arrows to both of the following deployment models and service models. There is then a line from these to cloud deployment technologies. Figure 12.20 cloud deployment models, cloud service models, and cloud deployment technologies are all considered for workload and service deployments. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. When examining workload and service deployments, there are three key architectural considerations. First, the deployment models in the cloud are evaluated, offering choices for where service models are deployed, such as public, hybrid, community, or private cloud environments. Second, the service model options are assessed to determine the level and type of services, including infrastructure as a service, IaaS, and platform as a service, PaaS. Each of these cloud service models will be discussed in more detail. Finally, workloads and services are actualized in the cloud using various deployment technologies, ranging from bare metal, i.e., high-performance physical servers dedicated to a single customer, where the burden of provisioning, maintaining, or scaling applications on these servers falls on the customer, to serverless computing, i.e., where customers deploy applications without the burden of provisioning, maintaining, or scaling these applications, as they are provided by the cloud service provider. These technologies serve as the foundation for executing cloud-based and cloud-native applications, allowing organizations to harness the benefits of cloud computing. Understanding these options empowers companies to select the most suitable approach, ensuring performance, deployment speed, scalability, portability, and security align with business requirements while managing costs effectively. Enterprises must consider different factors when deploying various workloads and services in a cloud environment. For instance, high-performance computing, HPC, demands significant compute and memory resources, whereas legacy applications may have lower resource requirements. Cloud service models. The three cloud service models, IaaS, PaaS, and SaaS, define a combination of information technology resources, e.g., compute servers, storage, memory, middleware, offered by a cloud provider and are not mutually exclusive. These service models change the way information technology, IT, resources are consumed. Traditionally, IT resources were purchased, managed, and maintained in a company's on-premises data center. The cloud computing service models, in contrast, provide a more economical solution where these IT resources are accessed and scaled on demand from a cloud service provider at a predictable cost. These service models are categorized as infrastructure as a service, IaaS, platform as a service, PaaS, and software as a service, SaaS. The following sections elaborate on these three cloud service models. Infrastructure as a Service, IaaS. Infrastructure as a Service, IaaS, is on-demand access to a cloud-hosted computing infrastructure that includes servers, storage, and network resources. These resources can be provisioned, configured, and used by the customer like on-premises resources are. The difference is the cloud service provider hosts, manages, and maintains these resources in its own data centers, as shown in Figure 12. 21. A diagram shown as a table includes on-premise, software platform infrastructure, and IaaS, software platform infrastructure. There is an arrow going down the left side of the column that reads Customer Manages, and an arrow going up the right side of the table that reads Cloud Service Provider Manages. Figure 12. 21 IaaS resources are managed by a cloud provider compared to on-premises resources that are managed by the customer. Attribution, copyright Rice University, OpenStax, under CC BY 40 license. IaaS customers access these resources via the internet and pay for these services on a subscription or pay-as-you-go basis. Infrastructure consists of three main components: compute for processing tasks, storage, and network. The compute component could, for example, include a general-purpose processing capability or more specific processing capabilities such as a high-speed graphics processor, GPU, or high-performance computing, HPC. The storage component could support different storage needs such as object storage, block storage, or file storage. Finally, the network component allows for the compute and storage components to communicate. IaaS resources are multi-tenant and are made available to multiple different customers simultaneously. The cost for the services varies depending on the technologies chosen. IaaS customers make use of these services on demand, where the demanded resources are provisioned and delivered to the customer in a matter of minutes or hours as opposed to days, weeks, or months, as is with traditional IT on-premises resources. IaaS also provides the flexibility for customers to scale up or down resources depending on their needs. Platform as a Service, PaaS. As discussed previously, IaaS is a set of compute, storage, and networking resources that have been virtualized by a cloud service provider and configured by the customer to suit their needs. PaaS takes advantage of all the virtualized resources from IaaS and adds to this. Platform as a Service, PaaS, is on-demand access to a cloud-hosted platform for developing, running, and managing applications by prepackaging middleware, language runtimes, and tools as containers. The cloud service provider hosts, manages, and maintains all the software included in the platform. This includes the servers, storage, and networking services. It also includes the operating system, middleware, and runtime environment. Figure 12.22 illustrates how PaaS customers can deploy their application and data. A diagram shown as a table includes on-premise, software platform infrastructure, and PaaS, software platform infrastructure. There is an arrow going down the left side of the column that reads Customer Manages, and an arrow going up the right side of the table that reads Cloud Service Provider Manages. Figure 12. 22 PaaS resources are managed by a cloud provider compared to on-premises resources that are managed by the customer. Attribution, copyright Rice University, OpenStax, under CC BY 40 license. PaaS generally makes it easy to get an application up and running quickly. PaaS is cost-effective in that customers don't have to bear the cost to manage the runtime environment for their applications. PaaS cloud providers generally provide tools such as DevOps and collaboration tools, as well as API marketplaces as services that could easily be integrated with applications. PaaS also provides the flexibility for customers to scale resources up or down depending on their needs. Software as a Service, SaaS. Software as a Service, SaaS, is a cloud-hosted, ready-to-use software or application that end users access with a client, e.g. web browser, desktop client, mobile app via a subscription model. SaaS takes advantage of all the resources from PaaS, but also includes the application and data, as shown in Figure 12.23. A diagram shown as a table includes on-premise, software platform infrastructure, and SaaS, software platform infrastructure. There is an arrow going down the left side of the column that reads Customer Manages, and an arrow going up the right side of the table that reads Cloud Service Provider Manages. Figure 12.23 SaaS resources are managed by a cloud provider, like PaaS resources, but they are subscription-based and include application and data. Attribution, copyright Rice University, OpenStax, under CC BY 40 license. Unlike IaaS and PaaS, SaaS has the highest level of abstraction, where the cloud service provider hosts, manages, and maintains all layers of the stack, including the application as well as all the infrastructure required to provide the application service. This allows for the SaaS application to always be upgraded to the latest version. SaaS applications are scalable at any level of the stack. Additional infrastructure resources such as compute power and platform resources, such as databases, can be added as needed. SaaS resources are also multi-tenant, where multiple users are all accessing the same pool of resources. Tenants would have access to the same hosted environment. However, they would have their own dedicated space to securely store their data. SaaS applications are cost-effective compared to the other cloud service models because the cloud service provider maintains and manages the entire stack. SaaS applications are also cost-effective compared to traditional applications hosted on-premises, where companies would have to bear the cost of the hardware, in addition to continued cost for IT support. One important benefit of cloud computing is automation. Depending on the service model chosen, organizations can reduce the layers of management of hardware, infrastructure, and applications. This reduces costs and effort of investment into these resources and allows organizations to focus more on innovation. For an organization to choose between the cloud service models and on-premises solutions, it must balance the level of complexity and effort of investment in each solution. These solutions present a spectrum from complex and high effort of investment to simple and low effort of investment, as shown in Figure 12.24. A diagram shows a comparison of on-premise, IaaS, PaaS, SaaS as a table with rows for each of these. Figure 12.24 complexity and level of investment effort decrease as level of abstraction from customer increases depending on the solution chosen. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. On-premises and IaaS solutions offer the greatest level of flexibility, but are the most complex and require more effort of investment. These solutions also increase costs as they require the hiring of systems personnel, as these solutions require a higher level of knowledge and management of infrastructure resources. Moving from left to right, PaaS solutions are less complex with less effort of investment and are generally managed by application developers. Finally, SaaS is the least flexible, but also the least complex and requires the least effort of investment. SaaS solutions are applications or software that don't require any installation or manual upgrading, and so the end user can be anyone. Many organizations use a combination of these solutions with the flexibility to change the service models used as their needs change. Cloud deployment models. Cloud deployment models dictate how cloud services are implemented, hosted, and accessed by end users. They revolve around the principle of virtualizing server, computing power into segmented, software-driven applications offering processing, storage, and networking capabilities. The following sections elaborate on various cloud deployment models, including private, community, public, and hybrid clouds. Public cloud model. A public cloud is a cloud deployment model where resources are remotely accessible by anyone offered through subscriptions or on-demand pricing plans. A public cloud deployment model is shown in Figure 12.25. This approach allows for the flexibility of provisioning resources on demand and pay only for what is consumed. Public cloud resources are owned and managed by the cloud service provider. This type of cloud hosting allows cloud service providers to provide various services to a variety of customers. A cloud service provider's resources are provisioned for any type of customer from individual users to major industry groups. A diagram shows PCs with lines connecting it to a cloud service provider and lines to other computers and buildings. Figure 12.25. A public cloud deployment model consists of resources accessible to all users. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Private cloud model. A private cloud is a cloud deployment model where resources are dedicated to one customer, such as a single organization for internal use, where cloud resources are accessed and managed by an organization. A private cloud deployment model is shown in Figure 12.26. It is not open to the public. Private clouds are isolated and contain the proper security to restrict access to them. They are protected with robust firewalls and a supervised secure environment. Private clouds could run on-premises, but can also run on vendor-owned data centers remotely. Private cloud resources are managed either internally by the organization or by a third party. Figure 12.26 shows two private clouds. a cloud service provider's secured resources are provisioned and dedicated to an organization. A diagram shows a cloud service provider, including various types of clouds, with lines from private clouds to dedicated private cloud to Organization 1 and dedicated private cloud to Organization 2. Figure 12. 26. A private cloud deployment model consists of dedicated resources with restricted access. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0 license. Community cloud model. A community cloud is a cloud deployment model where resources are only accessible by a selected group of organizations. The resources of a community cloud are mutually shared between the organizations that belong to a particular community or industry. Examples of community clouds are clouds for banks or governments. The community or industry members generally share similar privacy, performance, and security concerns. A community cloud consists of an infrastructure that integrates the services of different clouds to meet the specific needs of the community or industry. Community cloud resources are managed either by members of the community or industry or by a third party. Figure 12. 27 outlines a community cloud deployment model and shows two community clouds. A cloud service provider's resources are provisioned and dedicated to a community of organizations or government entities. A diagram shows a cloud service provider with lines from community clouds to dedicated to a group of government members and other lines to dedicated to a group of organizations. Figure 12.27. A community cloud deployment model consists of dedicated resources limiting access to a community. Attribution. Copyright Rice University, OpenStax, under CC by 4. 0 license. Hybrid cloud model. A hybrid cloud is a distributed computing architecture with two or more environments consisting of private and public clouds and on-premises infrastructure. A hybrid cloud deployment model is shown in Figure 12.28. This model provides greater flexibility compared to other cloud deployment models because it provides orchestration and management across all environments that lets customers run workloads wherever they need them, increasing workload portability across all cloud environments. A diagram shows PCs with lines to cloud service provider. There is another cloud also labeled cloud service provider. These are connected with a superimposed box labeled hybrid cloud. Two dedicated private clouds are shown connected to these clouds. Figure 12.28. A hybrid cloud deployment model combines two or more cloud deployment models. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Cloud deployment technology options. Cloud deployment technologies offered by cloud service providers include bare metal servers, virtual machines, VMs, and containers. The following sections elaborate on each of these deployment technologies. Another deployment technology that is available, however not widely used, are unikernels. Unikernels are also discussed in detail in the following sections. IaaS and PaaS are two service models through which these deployment technologies are provided. There are additional service models through which deployment technologies are provided. Containers as a service, CaaS, i.e. a version of IaaS where applications are deployed, managed, and scaled using a container-based virtualization, and serverless computing, also known as function as a service, FaaS. Figure 12.29 shows how PaaS and FaaS may leverage CaaS or IaaS for deployment. CaaS is positioned between IaaS and PaaS in the cloud computing stack. CaaS leverages the virtualization of compute, storage, and network resources from the underlying IaaS infrastructure. PaaS allows users to focus on application dependencies and runtime environments while having less control of the operating system and limited portability. CaaS, on the other hand, returns this control as it provides increased portability by facilitating operating system virtualization and customization in containerized deployments. A diagram shows the following flow. Function as a service, platform as a service, container as a service, infrastructure as a service. Figure 12.29 cloud deployment technology options are available when IaaS is leveraged by other service models, including FaaS, PaaS, and CaaS. Attribution, Copyright Rice University, OpenStax, under CC by 40 license. IaaS deployment options. Bare metal servers, VMs, unikernels, and containers are made available in an IaaS cloud service model. These deployment options offer a level of infrastructure control to address specific performance requirements, compliance considerations, and legacy dependencies. Bare metal servers offer the most control and flexibility, but with more overhead to maintain them. Moving from bare metal toward containers, the deployment options require less overhead because there is an increased level of automation that makes these options quicker and easier to provision or get up and running. They are also more portable. These four deployment options, in order of more control versus more portability, are illustrated in Figure 12:30. A diagram with four cells is shown. The labels of these cells are bare metal, virtual machines, unikernels, containers. Two arrows are below these cells. Under bare metal and virtual machines, the arrow points left and reads increase control. Under unikernels and containers is an arrow pointed right which reads increase portability. Figure 12:30 IaaS deployment options offer either more control or provide more portability. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Bare metal server. A bare metal server is a high-performance cloud server that is composed of a single tenant, non-virtualized physical server. Customers have complete control over the server's physical components of hardware, compute, and storage resources to optimize them to accommodate specific workloads. These servers may run any amount of work for the customer or may have multiple simultaneous users, but they are dedicated entirely to the customer. Virtual machines. A virtual machine, VM, is a virtualization of a computer system. The process of creating software-based, virtual versions of something such as compute, storage, networking, or applications is called virtualization. Virtualization is feasible because of a hypervisor, the software that runs on top of a physical server or a compute host that virtualizes it. Hypervisors virtualize the resources, such as CPUs, RAM, network, and in some cases, storage of the physical server. The hypervisor divides these resources while allocating what is needed for each operating system of a virtual server instance, VSI. The hypervisor, also referred to as a virtual machine monitor, VMM, is a software layer that lies between the physical hardware and the VSIs that run on top of it. The hypervisor allows for the scheduling of multiple VSIs with these divided resources. Thus, multiple virtual servers can run on a single physical server. Hypervisors also provide a level of security between VSIs so that data on one VSI is not accessible from another, maintaining isolation between them, as indicated by the dotted lines between the VSIs in Figure 12:31. A diagram shows the following flow: VSI1 OS1, VIS2 OS2, VIS3 OS3, hypervisor CPU RAM net store. Figure 12:31. Virtualization of compute resources via hypervisors is used to schedule VSIs. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Virtualization via hypervisors makes multi-tenancy of VSIs possible. This drives the cost of compute down. Physical servers individually can be quite costly. Virtualization is a cost-effective way to run multiple virtual servers on a single physical computer, thereby maximizing the utilization of resources and reducing cost. As shown in Figure 12:32, VMs run like a physical server that runs on a hypervisor. They can run their own different operating systems and are completely independent of one another. Running multiple VMs from one physical server also drastically reduces a customer's physical infrastructure footprint. VMs increase agility and speed because they can be provisioned quickly and easier with automation compared to provisioning an entire new physical server and environment. This also lowers downtime in case a VM unexpectedly fails because they are portable, as they can be moved from one hypervisor to another on a completely different physical server quickly. A diagram shows the following: virtual machines, App 1, binslibs OS1, App 2, binslibs OS Linux, App 3, binslibs OS Unix, hypervisor, host OS server. Figure 12:32. Multiple VMs are created and run on a hypervisor. Attribution. Copyright Rice University, OpenStax, under CC by 4.0 license. Unikernels. Originally introduced as Mirage OS, a unikernel is a single-purpose machine image that is compile-time specialized into a dedicated standalone kernel with only the libraries needed to run the application. Once deployed to a cloud platform, unikernels are protected against any modifications. Unikernels are built by compiling the application source code directly into a customized operating system that includes only the functionality required by the application logic, as shown in Figure 12:33. They are specialized machine images that run directly on a server's hypervisor or on bare metal. Unikernels are considered more secure, compared to other cloud deployment technology options due to their smaller attack surface. A diagram shows the following flow: configuration files, application binaries, language runtime, kernel threads, user processes, file system, network stack, compiles to unikernel, hypervisor, host OS. Figure 12. 33 multiple unikernels are built as specialized images and run on a hypervisor. Attribution: copyright Rice University, OpenStax, under CC by 4. 0 license. Unikernels provide all the advantages of VMs and containers while reducing the server footprint needed to deploy applications. Because unikernels offer a significant reduction in image sizes, have a reduced memory footprint, and greatly reduce the need for disk space. The unikernel's architecture increases agility and speed. They have minimal overhead, and because they have faster load times with lower latencies, they can start up very quickly, making them faster than containers and VMs. Unikernels are also very portable. Their small size makes it easier and more cost-effective to move them from one hypervisor to another. The adoption of unikernels remains low due to a combination of lack of awareness and low availability of orchestrators. They are becoming more prevalent in single-purpose devices such as network function virtualization, NFV, appliances. However, data center adoption remains low. Containers. Containers are a form of operating system virtualization that is more efficient than hardware virtualization because they utilize a full system hardware virtualization. In contrast, containers leverage and run on a single instance of an operating system where the virtualization is managed by the host operating system, as shown in Figure 12.34. A diagram shows the following: containers App 1, App 2, App 3, container engine, host OS server. Figure 12.34. Multiple containers are built and run on a container engine. Attribution: copyright Rice University, OpenStax, under CC by 40 license. While VMs run as isolated servers on a hypervisor, containers share the same operating system and kernel of the host server. It appears as if each container runs on its own operating system and contains all the required binaries, libraries, and application code that is needed to run the application deployed in it. This is possible because containers run as isolated processes, making it possible to run many containers on a single bare metal server, or VM, without any interference between them. Containers access shared resources of the operating system, but also remain as isolated processes because the shared kernel manages process isolation. Namespaces and control groups, C groups, also help provide the illusion of process isolation. Namespaces allow for the customization and the appearance that each container instance has its own operating system. Control groups, on the other hand, monitor and manage shared resources controlled by the containers, which helps significantly reduce the number of compute instances needed to run applications. Container deployment options include building your own container service, utilizing off-the-shelf containers as a service platforms, or choosing managed container services, such as managed Kubernetes, provided by large cloud service providers, CSPs. A container as a service, KaaS, is a type of IaaS specifically geared toward efficiently deploying, running, scaling, and managing a single application using a container-based virtualization. Container deployment using the Build Your Own Service option requires the customer to manage the container technology, container scheduling and orchestration, as well as cluster management. Customers deploy the containers on top of IaaS, either bare metal or VM. The CSP, however, manages the underlying infrastructure. Container deployment using an off-the-shelf KaaS platform requires the customer to containerize the middleware, libraries, and applications or microservices. Customers deploy the containers on-premises or in a public or off-premises private cloud environment. This option has a higher overhead for the customer compared to PaaS because the customer is responsible for creating and updating the container images for each of these components. Container deployment using the Managed Container Services option requires the customer to manage the workload. The CSP manages the container environment as well as the underlying infrastructure. PaaS deployment options. The cloud deployment technologies that are provided through IaaS deployment options are also provided through PaaS deployment options. In addition to the infrastructure provided, PaaS deployment options also provide the operating system, middleware, runtime, and other infrastructural components that also need to be managed with IaaS. PaaS thus offers a fully managed solution for developers to quickly deploy and launch their applications, significantly reducing infrastructure and middleware overhead for developers. This allows developers to focus on developing and deploying their applications, while the burden of managing the infrastructure, back-end services, and any other system administrative services falls on the cloud service provider. FaaS deployment options. Function as a service, FaaS, and serverless computing are mostly synonymous. In the cloud-native development model of serverless computing, developers can build and run applications, but are not responsible for provisioning, maintaining, and scaling the server infrastructure, as this is outsourced to the CSP. The customer is thus focused exclusively on the business logic of the application. As shown in Figure 12.35, navigating up the y-axis towards serverless computing customers focuses more on the business logic and writing the application code abstracting from the underlying infrastructure. Navigating the x-axis towards serverless computing decreases stack implementation, and customers have less control of how the application is deployed. A diagram shows two arrows. One goes up and reads Increase Abstraction App Development Focus. One goes right and reads Decrease Flexibility Stack Implementation. Between these arrows is the following flow. Bare metal virtual machines, containers serverless. Figure 12.35 serverless computing provides the highest level of abstraction from the infrastructure with a focus on application development. Attribution. Copyright Rice University, OpenStax, under CC BY 4.0 license. Serverless computing offerings typically fall into two groups, Backend as a Service (BaaS) and Function as a Service (FaaS). Backend as a Service (BaaS) is any third-party service that can be integrated with an application where the BaaS code does not need to be managed, and there are no servers. BaaS gives developers access to a variety of third-party services and apps. For instance, a cloud provider may offer authentication services, extra encryption, cloud-accessible databases, and high-fidelity usage data. With BaaS, serverless functions are usually called through APIs. More commonly, when developers refer to serverless, they are talking about a FaaS service model. Function as a Service, FaaS, is a compute platform for serverless where developers can run functions that are single units of deployment of the code, which is run by events. They are typically invoked via an API gateway. An API gateway translates requests to a single endpoint and then routes it to a FaaS function. FaaS/serverless functions have the following basic characteristics. An event-driven architecture, provided by the cloud service provider, is an architecture where functions are invoked by an event. The function may initiate other events, which could invoke other functions. Functions that are a single unit of deployment of the code and configuration run in a managed environment. Functions are executed in the cloud and run in ephemeral stateless containers. Link to learning. Read this article about serverless architectures for more information. With FaaS/serverless computing, the cloud service provider manages the infrastructure in its entirety. The FaaS/serverless underlying infrastructure is automatically scaled as demand increases. FaaS/serverless solutions have a faster time to market. Customers are not responsible for the management of any of the underlying infrastructure, making it easier to build and deploy FaaS solutions faster and bring them to market. FaaS/serverless is a polyglot environment. FaaS functions can be written in any language if it is supported by the cloud service providers. FaaS/serverless solutions are inherently highly available. FaaS/serverless solutions can be deployed across multiple availability zones in different geographical regions. Cloud service providers manage fault tolerance and deployment across the available regions, making the FaaS/serverless solution highly available. Serverless offerings are usually metered on demand through an event-driven execution model. Customers pay for execution only. When a serverless function is idle, there is no cost. Customers must, however, be aware that providers place limits on the resources available to functions, processing time, and concurrency of event processing. These constraints must be assessed to ensure the user experience is not degraded. Link to learning. Learn more about use cases for using a serverless architecture in 3 specific application areas: PaaS and FaaS comparison. PaaS provides a platform that allows customers to provision and scale the infrastructure needed as well as develop, run, and manage applications, without the complexity of managing the underlying infrastructure required to run the application. FaaS goes a step further in that it provides an environment where developers can focus on running and managing code without having to provision resources or scaling the underlying infrastructure. In summary, both FaaS and PaaS provide an infrastructure managed by the cloud service provider. Both provide scalability options. Both deliver high availability from remote infrastructure managed automatically by the cloud service provider at scale. FaaS/serverless and PaaS on the surface appear to be very similar in their implementation and use from a development point of view. In reality, these two cloud deployment services are quite different. Scalability, pricing, startup time, tooling, and the ability to deploy differ between the two platforms. Serverless applications offer true auto-scaling capabilities to customers without any additional configurations. PaaS provides scalability options that are more advantageous compared to deployments on bare metal servers. However, developers still must consider how to construct and scale a PaaS platform. They must forecast resource capacity and configure PaaS-hosted applications to scale up and down based on demand. Serverless cost structure is based on usage, and there are no fixed monthly charges for services. With FaaS, customers pay per event-based invocation of the function only. With PaaS, pricing models differ depending on the PaaS provider and are generally associated with the use of compute, storage, and network resources costs. This means for PaaS, costs accrue during idle time. In some cases, serverless can be a more cost-effective option for software deployments. FaaS functions execute in response to events, offering rapid startup times crucial for event-based processing. Conversely, PaaS applications lack event-triggered startup capabilities and are tolerant of slower startup times due to their long-lived nature. FaaS abstracts the application layer, allowing developers to focus solely on function code, while cloud service providers manage other aspects. This abstraction, however, reduces flexibility, as developers must adhere to provider-specific frameworks and language limitations. PaaS, on the other hand, offers developers greater control over the development environment, including the choice of programming languages and frameworks. There are at least 3 application areas where it makes sense to go serverless: unpredictably fluctuating workloads or frequent low-usage ideal for the pricing model of FaaS/serverless solutions. Processing large, distributed data sources because of the feasibility of auto-scaling of FaaS/serverless environments where computing performance can be dramatically boosted. Building highly modular solutions, potentially incorporating external services that can also exploit the pricing model of FaaS/serverless solutions. More generally, serverless architecture is ideal for asynchronous, stateless applications that can be started instantaneously. Likewise, serverless is a good fit for use cases that see infrequent, unpredictable surges in demand that are high volume and with parallel workloads. An example of an infrequent in-demand task would be a batch processing of incoming image files. This task can be high volume if a large batch of images to be processed arrives all at once. Serverless is also a good fit for use cases that involve incoming data stream processing for implementing applications such as chat bots, scheduled tasks, or business logic. Some other common serverless use cases are backend APIs and web apps, business process automation, serverless websites, and integration across multiple systems. CSPs offer several serverless services. Understanding the minute differences between these services can be overwhelming, making it challenging to select the set of services to develop an optimal serverless architecture. It is expected to invest upfront time to get familiar with these services, to understand the runtime expectations and resource consumption associated with a prospective serverless solution. It is also challenging to maintain a serverless architecture in a continuous deployment procedure. There are many cloud deployment technology options available to customers, which will continue to evolve. The vast possibilities available provide support for a wide host of services. The sections that follow provide insight into common use cases that are associated with the use of these deployment technology options. Industry Spotlight. CaaS, PaaS, or FaaS deployment technologies are broadly used in the industry today to deploy cloud-native applications. Containers/CaaS, PaaS, and FaaS/serverless deployment technologies are used by Netflix, Uber, and WeChat to deploy cloud-native systems that consist of many independent services. Knowing these systems, can you elaborate on the suitability of containers/CaaS as compared to PaaS or FaaS/serverless for these particular systems? Cloud deployment technology, use cases, and implementation. There are various types of situations that prompt the use of cloud deployment technologies. The corresponding use cases and their implementation are covered in the following sections. Cloud deployment technology use cases. The most common types of deployments are for enterprise data centers, which will be the focus of these use cases. Typically, multiple cloud deployment technologies are used together to provide the services and deployment requirements to satisfy customer needs. As customers seek to deploy large-scale enterprise applications, they must assess the required infrastructure, middleware, runtime dependencies, and constraints to choose the most appropriate cloud deployment technologies. For cloud-native applications, cloud deployment technologies such as KS, PaaS, and FaaS are the most popular. Bare metal deployment technology. With bare metal servers, there is no virtualization and no hypervisor overhead, thus their resources, CPU, memory, and I/O, are dedicated to the application deployed on it. These resources, along with the hardware, are highly customizable and can be tuned up for maximum performance, making bare metal servers a viable option to support resource-intensive workloads such as HPC. This also helps with latency-sensitive applications, e.g., streaming services and large databases that consume significant resources. A combination of cloud deployment technologies can be used to satisfy the various requirements of a solution architecture. Bare metal servers can be used for the resource-intensive components, whereas VMs, containers, and other cloud deployment technologies deliver application services. Bare metal servers are also an option for legacy applications that may not be virtualized or not well suited for a virtualized environment. Bare metal servers are also a good fit for security-oriented applications because additional security measures can be easily integrated. Bare metal servers are the best fit for solutions that must comply with regulations or contract agreements that require single-tenant hosting, VMs deployment technology. Legacy applications that can be virtualized but have known and manageable behavioral issues are well suited for cloud deployment using VMs. This also applies to legacy applications that are not well documented, but there is basic knowledge of how they run. VMs are a viable option for monolithic and tiered applications that are not mature enough to be migrated to a microservices architecture. Such applications could be migrated to the cloud as cloud-based monoliths. VMs can also be used to provide enhanced container security, although with additional overhead. The use of a VM can provide an additional layer of isolation when deploying containers, eliminating the use of a shared kernel model. Containers/KS deployment technology. Containers enable scaling, replicating, and choreographing services in a microservices architecture. Containers are also lightweight, portable, and platform independent. The ability to start containers in a fraction of the time of VMs is critical. With these advantages, cloud customers have developed a plethora of microservices ranging from user interface, UI, front ends to back-end microservices. A microservices architecture is a good use case for using containers. Legacy applications that depend on out-of-support operating systems or other out-of-support dependencies are candidates for containers. Application dependencies can be containerized to enable execution. However, there are limitations to this approach, and it can be very challenging to get such applications up and running in a container. The application dependencies must be assessed to ensure containerization is a viable option. Legacy applications that can be modernized and migrated to the cloud are also good candidates for containers. Platform flexibility is the primary use case for KS. Containers can consistently run anywhere without the limitations of middleware and platform tools offered by PaaS platforms. KS provides the customers with a container-based environment they can control security, scalability, and availability without significant effort. Unikernels deployment technology. The need to optimize VMs is the most common use case for unikernels at this time. Unikernels have smaller footprints in part because they are built without unnecessary binaries and libraries. Because they have less overhead, unikernels can start up very quickly, faster than VMs and containers. With the smaller footprint and speed comes improved security when it comes to unikernels. Because unikernels are built to include only the libraries needed to run the application, this reduces the cybersecurity attack surface, thereby making them more secure compared to the other cloud deployment technologies. Mutable server infrastructures are where servers are continually updated and modified in place even after they are deployed. Immutable infrastructures are where servers are never modified after they are deployed. The main difference between mutable and immutable infrastructures is the policy used that determines whether components of the environment are designed to be changed after deployment. Customers may need or expect an immutable infrastructure to preserve the integrity of an environment, Although VMs are not permitted in an immutable environment, unikernels, by design, protect against such modifications because any updates or changes to any components are built from an image and provisioned to replace the old ones. Unikernels, thus, are a good choice for the need of an immutable infrastructure. PaaS deployment technology. PaaS is used to deploy modern, cloud-native application architectures. PaaS provides a complete cloud platform that includes hardware, infrastructure, middleware, and runtime environment. It is most often delivered using a container-based infrastructure and therefore supports the same use cases as containers. The most prevalent use case for PaaS is speed to market. PaaS reduces or eliminates the burden of deploying and managing infrastructure, enabling cloud customers to focus instead on customer needs and development of the applications. PaaS can be more affordable, especially for software development houses, which often do not have the budget to hire personnel to build and manage infrastructure, as it offers access to a wider range of services up and down the application stack. PaaS also provides a cost-effective way for customers to scale up and down resources as needed. PaaS also provides a development and CI/CD environment to quickly develop, integrate, build, and deploy applications. PaaS deployment technology. The use case for PaaS/serverless is limited to microservices-based applications, more specifically applications that are short-lived and event-based. Examples of services include data stream and image processing, reservation handling, and IoT data processing. Other use cases include high-volume and parallel workloads and data aggregation tasks. PaaS/serverless is used to reduce the customer's responsibility to manage middleware dependencies, runtime considerations, and the underlying infrastructure. The PaaS/serverless platform takes care of this, leaving the customer with the responsibility to write the function code. The result is increased velocity in delivering highly available technology capability and satisfying business demand. Cloud deployment technology implementation. There are several tools cloud customers must consider when implementing services using the cloud deployment technologies discussed earlier. Cloud customers who adopt automation will increase deployment speeds while lowering costs. With the growth of cloud environments, customers must manage increasingly complex environments. There are several tools that can be used to automate tasks, such as server provisioning and configuration management. Automating these tasks improves the efficiency of DevOps teams and speeds up the deployment of services because they reduce the volume of manual tasks required to manage cloud resources and infrastructure. Tasks that must be automated in the case of each cloud deployment technology include the IaaS tasks of orchestration and provisioning. PaaS tasks include source code management and CI/CD pipelines, and PaaS/serverless tasks include orchestrating the deployment of functions and their dependencies. Automation tools help customers reduce operational costs and minimize errors. Automation tools can be used to configure and install containers, VMs, or other systems, provision and deprovision resources for auto-scaling, and allocate resources to optimize workload performance. There are several tools that are available to assist with automation of development, delivery, and management of applications, workloads, and infrastructure. Tools such as Ansible, Pulumi, or Terraform can help with automating orchestration. Tools such as Ansible, Chef, Puppet, or Salt can help with automating configuration management. Tools such as Bitbucket, GitHub, or GitLab can help with automating source control management. Tools such as Broccoli, CircleCI CodeShip, or Maven can help with automating builds. Tools such as Bamboo, CircleCI, CodeShip, and Jenkins can help with automating continuous integration. For automating continuous deployment, additional options include Go, Julu, or Octopus Deploy. Global issues in technology. DevOps across the globe. While cloud-native applications are deployed all over the world, they involve the use of DevOps methods and tools that are mostly developed in the United States or Europe. For example, DevOps refers to terms like CI/CD, which relate to terms, i.e., continuous integration, continuous deployment, and tools, e.g. Jenkins, GitLab, Docker, that are respectively used and implemented by companies in the United States. Therefore, it is not certain how well those methods and tools work in other cultural contexts. What is your opinion regarding these concerns? IaaS Cloud Deployment Implementation. When adopting IaaS, ISC can be used to automate infrastructure management provisioning by using code instead of manually. This includes managing servers, managing operating system installations and updates, kernel modifications, and the management of storage and other infrastructure components needed for the development and deployment of applications. Orchestration tools, e.g., Kubernetes, can be used on any of the cloud deployment technologies discussed to automate services, such as allocating resources and scaling applications as needed. Configuration management tools, e.g., Ansible, can also be used on any of the cloud deployment technologies to automate the process of configuring and managing changes to these resources. Both orchestration and configuration management tools provide support for integrating with IaaS services provided by the major cloud service providers, e.g., Amazon Web Services, Google Cloud Platform, IBM Cloud, and Microsoft Azure. Link to learning. Learn more about infrastructure as a code, as well as design principles for ISC and design patterns for infrastructure deployment stacks. PaaS Cloud Deployment Implementation. As mentioned, PaaS also provides services for managing the operating system, middleware, and runtime environments for applications. As such, available PaaS tools are used for automating tasks, such as streamlining code integration between systems, as well as managing application build and deployment processes. A tool discussed earlier, Tanzu, provides a major improvement over traditional PaaS deployment options by enabling deployment on any cloud that provides a container orchestration mechanism. It is equivalent to an application server for the cloud that can deploy cloud-based and cloud-native application workloads on any cloud. PaaS deployment technology implementation. When adopting PaaS, applications are deployed on server infrastructure in response to events without customers having to manage the underlying infrastructure. Although the managing of the infrastructure is not the customer's concern, there are setup requirements customers must deal with, including setting up the serverless runtime environment, deploying serverless functions, cloud service dependencies, e.g., storage, and the required amount of memory needed. There are tools, e.g., Ansible, that are available to help deploy these cloud services. Cloud management platforms, CMPs, are used to simplify the deployment and management of cloud services across various cloud service providers. Customers manage several large-scale applications in very complex environments using services from multiple cloud service providers. CMPs can be helpful in simplifying the deployment and management of all these services. Understanding the common use cases, as well as the available cloud deployment technologies, available help customers to select the appropriate solutions to support their needs. Selection of cloud deployment technologies. When selecting the most appropriate cloud deployment technologies, customers should both strategically and tactically consider these choices. Strategically, customers should consider their business needs and select the cloud deployment technologies that are relevant to meet these needs. Tactically, customers should consider the application requirements and relevant cloud services needed to support those applications. In summary, the steps to select the appropriate cloud deployment technologies include: assess how well the cloud deployment technology options meet the business needs. Understand infrastructure and workload service requirements. Select cloud deployment technologies that satisfy the application requirements and provide the services needed, fit to business needs. With so many cloud deployment technology options, customers should regularly assess these options with the following considerations in mind. Cost. Understand the different cost models associated with the various cloud deployment technologies. Architectural fit. Understand the application deployment needs and how the different cloud deployment technologies support those needs. Performance. Understand the application performance requirements, e.g., workloads performance requirements, bandwidth requirements, latency requirements, and how the different cloud deployment technologies satisfy these requirements. Compliance. Identify any specific regulatory or contractual requirements that impose limitations that can impact the choices of cloud deployment technologies. Elasticity requirements. Identify the level of elasticity needed to satisfy the possible need to grow or shrink infrastructure resources dynamically as needed. Control requirements. Determine the level of control required to manage the various cloud deployment technologies and at what layers of the infrastructure. Cloud service provider lock-in. For customers who manage diverse, complex environments across multiple cloud service providers, determine the level of portability needed to enable the flexibility to change providers to optimize services utilized. Although generally there is no formal process for selecting cloud deployment technologies, customers can benefit from a more formalized process as it allows customers to implement the appropriate orchestration and management tools and establish processes needed to deliver effective and efficient services. Understanding workload service requirements. When selecting cloud deployment technologies, requirements, e.g., latency limitations, industry-dependent data protection controls, related to the types of workloads or services should also be considered. Selecting application, service, cloud deployment technology. As the strategic requirements and workload service constraints discussed previously are defined, customers can then evaluate the cloud deployment technologies that are most appropriate to meet their business needs. The cloud deployment technologies selected must adhere to the service levels required to satisfy business needs. These options may change over time as the range of available cloud deployment technology options continues to evolve. Prudent customers should proactively periodically evaluate these cloud deployment technologies to continuously meet business needs. Applications composed of multiple cloud services. A cloud mashup is a technique for seamlessly combining multiple cloud applications from several sources into a single integrated solution. Cloud mashups can be realized in many ways, covering different scopes depending on the purpose of the mashup. For example, PaaS services on public clouds can be used to create innovative cloud-based and cloud-native applications as cloud mashups, which enable corporations to undergo digital transformations to provide competitive solutions while differentiating themselves. An example of a cloud mashup that provides a driving route recommendation service is the mashup of AWS EC2, Facebook's authentication and authorization services, and Google's MapReduce services. The selection of cloud deployment technologies is an important factor in the overall quality of cloud mashups, measured by quality of service and quality of experience assurances, as these metrics specify the desired performance requirements of the cloud mashup. Regarding the previously mentioned driving route example, the recommended driving route and the speed at which the route is calculated are important factors to determine the quality of this service. In addition, the discovery of the best choice web services and the streamlining of services into a mashup are also impacted by the selection of cloud deployment technologies. The increasing demand for innovative cloud services have led to cloud service providers competing to provide mashup service discovery, automated composition techniques, and reusable cloud components, APIs as services that support the ability to quickly assemble mashups. Technology in everyday life. Real life and technology. How does the use of cloud deployment technologies help people in everyday life? As was mentioned, cloud deployment technologies can be used to create cloud mashups. One example discussed is a driving route recommendation service, the mashup of AWS EC2, Facebook's authentication and authorization services, and Google's MapReduce services. Many people depend on a driving route recommendation service in GPS systems today. It was also mentioned that the selection of cloud deployment technologies directly impacts the overall quality of the cloud mashup, as the accuracy of the recommended routes and the speed at which routes are calculated are important features of such a service. Can you think of other ways cloud deployment technologies help people in everyday life? Provide a couple of illustrative scenarios to explain your opinion. Key to success summary. There are lots of options when it comes to choosing the most appropriate cloud deployment technologies, and these options will continue to grow. Customers should understand the options that are available and how these cloud deployment technologies can best fit the requirements of deploying their applications to the cloud. To help select the most appropriate options, customers should consider: 1. Understand how the currently available cloud deployment technologies and services work and fit in the delivery of cloud services. 2. Identify the tools available to automate and support the delivery of these cloud services. And 3. Assess the technical factors, e.g., application architecture, data implications, runtime dependencies of these cloud deployment technologies, and select the technologies that provide the best fit to their business needs. These steps should be repeated periodically to reassess the available cloud deployment technologies as these technologies evolve and more are added. Customers should keep in mind that the benefits of researching the most appropriate selection of cloud deployment technologies to fit business needs up front can significantly outweigh the costs of taking an ad hoc approach of combining technologies that may end up providing a suboptimal user experience. Think it through. Which solution to select? Given the fact that many deployment technologies are available today, is there a process that facilitates the selection of these technologies to deploy cloud-native applications? Learning objectives. By the end of this section, you will be able to understand how to deploy a cloud-native application on a PaaS platform, understand how to deploy a cloud-native application using VM, where Tanzu understand how to deploy PaaS functions on a serverless platform. This module focuses on building sample applications that illustrate the steps taken to deploy sample applications using various cloud deployment technologies. The first section focuses on how to build a sample cloud-native application on a PaaS platform. The sample application provided illustrates the use of microservices, Docker containers, and Kubernetes orchestration. The second section focuses on how to set up a suite of products that are used to manage Kubernetes clusters and monitor applications that are deployed in Kubernetes clusters. Finally, the third section focuses on how to deploy PaaS functions that are parts of a distributed application on a serverless platform. The example provided illustrates the use of various metrics and performance dashboards used to monitor a distributed application. When working through these examples, keep in mind that they are based off tutorials that are made available by the cloud service providers. As the technologies used in these tutorials evolve, the tutorials may change. As a result, there may be differences in the configuration options in the cloud service provider consoles, or some of the steps may have changed. Regardless, the underlying goals of these examples should remain achievable. These examples also require subscriptions to AWS and Microsoft Azure. All cloud services providers provide free trial credits. These examples were completed without exceeding the free trial credit and using as many free tier services as possible. PaaS deployment of a sample cloud-native application. The example in this section illustrates PaaS deployment of a cloud-native application on Microsoft Azure. A subsidiary of Microsoft, Azure is a cloud computing platform that offers a wide range of services that allow customers to build, deploy, and manage applications and services in the cloud. The sample cloud-native application 13 includes 2 microservices. Both communicate with a single data store. Each microservice is containerized and deployed in a Kubernetes environment, illustrating Kubernetes orchestration. The PaaS deployment of this sample cloud-native application in Azure is illustrated in Figure 12:36. A diagram shows the following flow. Application Docker build push Azure Container Registry, pull Azure Kubernetes Service Container. Figure 12:36. A cloud-native application is deployed in Azure. Attribution. Copyright Rice University, OpenStax, under CC BY 4.0 license. One microservice implements a web service in JavaScript using Node. Express.js is used to implement the REST API for the web service. Express.js is a backend Node web application framework used to implement REST-TFL APIs. This microservice pushes data updates to a data store via the REST API. The other microservice implements a web service using Next.js. Next.js is an open-source React framework used to create full-stack web applications. React is a library used to create components to render to certain environments, including web and mobile applications. This microservice reads data from the same data store. Docker images are created for each microservice and pushed to an image registry. Azure's Container Registry Service, ACR, is used for this purpose. Each microservice is self-contained and encapsulated into Docker containers that are pulled from ACR and deployed into worker nodes in a Kubernetes cluster. Scaling the microservices is managed by Kubernetes. The Azure Kubernetes Service, AKS, is used for this purpose. Both microservices communicate with a single data store. The data store used is a PostgreSQL database hosted in Azure. Prerequisites: open a web browser and log into the Azure portal. The Azure portal is a web-based console that allows customers to manage their cloud services and Azure subscriptions. An Azure Resource Group. An Azure Resource Group is a container that holds related resources used in a cloud solution. In this example, the resource group RG-Native Ipsistis is used. Set up a Postgres database in Azure. The first step is to create a data store that both microservices will communicate with. Azure Database for PostgreSQL is the resource used for this purpose. The following steps create a Relational Database Management Service, RDBMS. Once the RDBMS is created, a PostgreSQL database is created along with tables to store the data. Finally, data is inserted into the database. Create the resource in the Azure portal. Search for Azure Database for PostgreSQL. Select Azure Database for PostgreSQL listed under the Marketplace section. Select Azure Database for PostgreSQL Flexible Server for the resource type and click Create. On the Basics tab, configure the resource attributes. Table 12. 1 shows the list of settings that should be used. Any settings not included in the table should be set to the default values provided in the wizard. Basics tab settings subscription, select the default subscription. Resource group for this example, RG native ipsistis is used. Server name, enter a unique name for the resource. For this example, NaughtyB serverflex is used. Data source select none. Location for this example, select the region that is used for the resource group. Version select 11. Compute plus storage, click on the configure server link. On the configure blade, select basic, set the vcore value to 1 and storage to 2 GB, and then click save. Admin username, enter a username. For this example, student is used. Password, enter a password. For this example, PA55W01234 is used. Table 12. 1 configuration for the PostgreSQL database to create the resources as configured in the table 12. 1. Click Review plus Create and then click Create. The provisioning of the database server may take several minutes. A status message appears when the deployment is complete. Click on Go to Resource. Configure connection security policies need to be added to allow resources, including all microservices, to connect to the data store securely. This step configures the connection security settings so that the microservices can securely connect to it. This is done on the connection security page for the data store resource. From the menu on the left under Settings, click Networking. Enable the database server to allow connectivity from the cloud-native application deployed and running in Azure. To do this, click Yes for Allow access to Azure services. Immediately below this configuration, click plus Add current client IP address, figure 12, 37. A screenshot shows the connection security settings for microservices, figure 12. 37. It is important to configure the connection security settings so that the microservices can securely connect to it. Used with permission from Microsoft, for this example, disable the SSL settings. If this step was missed before provisioning the database, do the following. Click Server Parameters. In the search field, search for Require Secure Transport. Click off Figure 12, 38. A screenshot shows how to disable the SSL settings. Figure 12, 38. Be sure to disable the SSL settings. Used with permission from Microsoft, click Save. From the menu on the left, click Overview. Make a note of the server name and admin username values. These values are used to connect to the database from the cloud-native application deployed and running in Azure. Create the database, tables, and initial data. The data store is now configured with a valid hostname and user account. The next step is to create a database and tables for the data to be stored. Once the database and tables are created, initial data is inserted. Open the Azure Cloud Shell. To do this, click on the Cloud Shell icon to the right of the search bar in the Azure portal. In the bottom frame of the browser page, the Cloud Shell will load. Click Bash if prompted when the Cloud Shell loads. Click Create Storage if prompted to complete loading the Cloud Shell. In Cloud Shell, connect to the database with the following PSQL command. Insert the server name and admin username values obtained earlier for server name and username, respectively as shown below. A Postgres command prompt appears. PSQL host equals server name, port equals 5432, username equals username, DB name equals Postgres. Create the database. Create a table and insert data that will be used in this example. Run the SQL statement below to create a new PostgreSQL database. The database name used in this example is SceneInventory. Create database SceneInventory. Run the command below to switch to the newly created database. This step is necessary so that the tables are created in the correct database. \c SceneInventory. Run the SQL statement below to create a new table. The table created for this example is inventory. It contains 4 fields: id, which is the primary key, name, quantity, and date. Create table inventory, id serial primary key, name varchar 50, quantity integer, date not null default now. Date, confirm the inventory table was created using the following command. \dt insert data into the inventory table with the SQL statements below. Insert into inventory, id name, quantity values 1 yogurt 200. Insert into inventory, id name, quantity values 2 milk 100. Confirm the data was successfully inserted with the following command. Select from inventory. The output lists the data records. Type \q to disconnect from the database. Create and deploy a cloud-native application now that the data store for the cloud-native application has been successfully created and configured. The next step is to create each of the 2 microservices of the cloud-native application. As previously mentioned, the cloud-native application consists of two microservices. One of the microservices is implemented using Node Express, JS. This microservice serves as a backend service. The second microservice is implemented using Next, JS, and serves as a front-end web service. Although these microservices do not directly communicate with each other, both communicate with the data store. Create the backend service. The first microservice created is the backend service. This service exposes a set of functions that can receive requests via a REST API that inserts inventory data into the data store. Open the Azure Cloud Shell. To do this, click on the Cloud Shell icon to the right of the search bar in the Azure portal. In the bottom frame of the browser page, the Cloud Shell will load. Click Bash if prompted when the Cloud Shell loads. Click Create Storage if prompted to complete loading the Cloud Shell. Create a directory for the application and navigate into it with the following command. mkdir pkn node express and in cdkn node express, use the command to initialize a node project. A package JSON file among other files is generated for the node project. The package JSON file is updated to include dependencies for the Node Express, JS backend service, npm init yexpress. JS is used to build the REST API for the backend service. Install Express, JS with the following command. Confirm the package. JSON file is updated listing Express as a dependency. npm install Express create a new file named index, JS with the command code index, JS and add the code shown below. To save the file, type ctrl plus s close the file by typing ctrl plus q. The code creates an Express application server that listens on port 8080. It accepts client requests sent in JSON format. Const express equals require, express, const port equals process, env. Port letter 1C1 8080 const app equals express, app, use express, JSON, app, listen port, equals console, log sample app is listening on port. Connect the cloud-native application to the database. Now that the backend service has been successfully created, the next step is to add code to the Express JS application that allows it to connect to the data store. The Object Relational Mapping (ORM) technique converts a data object in the Express JS code to a table in the PostgreSQL relational database. Sequelize is used for this purpose. In Azure Cloud Shell, run the command below to install the Sequelize package. npm I sequelize pgpghstore edit the index JS file to add code that allows the Express JS application to connect to the scene-inventory database. Insert the code below. Substitute the server name value for server name appears twice. This code provides the connection hostname and user account to the data store so that the backend service can connect to it. Const sequelize equals require, sequelize. Const sequelize equals new sequelize, Postgres, student server name, PA55W0 1234 at server name. Postgres database, Azure, com 5432/scene inventory, sequelize, authenticate, then equals console. Log connection has been established successfully. Catch error equals console. Error unable to connect to the database. To use sequelize in the Express JS application, add the following code to the file the index.js. This is the code that does the mapping between data objects in the Express JS code to data records in the database table. The variable inventory is declared to define the mapping between the Express JS code and the inventory table. Notice how this definition contains the exact same fields that were declared in the inventory table in the scene inventory PostgreSQL database when it was created. Const inventory equals sequelize. Define inventory, id, type sequelize. Integer allow null, false, primary key true, name, type sequelize. String allow null, false, quantity, type sequelize. Integer date, type sequelize. DATONLY default value. Sequelize now, freeze table name, true, timestamps, false. Create the Express JS REST API endpoints. Now that the Express JS application is configured to access the PostgreSQL database, the next step is to create the REST API to accept client requests. These REST routes call functions that perform read and write operations on the PostgreSQL database. Two Express JS routes are added in the code. The first route performs a read from the database in response to receiving a GET HTTP request. The second route performs a write to the database in response to receiving a POST HTTP request. Edit the index.js file and add the code shown. The code adds a route that accepts HTTP GET requests to fetch an inventory record. The ID for the record is included in the request, and the ID, name, quantity, and date fields for the inventory record are returned. App get/inventory/id async rec res equals const ID equals rec params. Id try const inventory equals await inventory. Find all attributes ID, name, quantity, date, where id raise, JSON, inventory, catch error, console. Error, add the second root by adding the following code to the index.js file. The code adds a root that accepts HTTP post requests to create a new inventory record. Values for the record are included in the HTTP request body with exception for the date, which is calculated from the current date. App post/inventory async rec raise equals try const new item equals new inventory rec. Body await new item save raise JSON inventory new item catch error console. Error create the front-end component. The second microservice created is the front-end web service. This web service provides a web-based user interface to fetch inventory data. In the Azure Cloud Shell, use this command to create a Next.js application. npx create next app answer the prompts. It is important to select No for the app router prompt. Note that the project name is CNA Next. This is the root directory for the Next.js application. Navigate into the CNA Next directory. Recall in the backend, Express.js application SQLize is used as the ORM to convert data objects in the Express.js code to data records in the inventory table in the database. Prisma is a node ORM used to map data objects to tables in a relational database. Install the Prisma and Prisma client packages with the following commands. npm install Prisma, npm install Prisma save dev, npm install at Prisma/client configure the Next.js application to use Prisma by running the command. This creates the Prisma/subdirectory and generates the schema, Prisma configuration file inside it. This command also generates a dotenv file in the root directory of the project. npx Prisma init in the Prisma/directory, edit the generated schema, Prisma file and add the content shown in figure 12.39. This adds the data model for the inventory table. A screenshot shows the data model for the inventory table. Figure 12.39. This content adds the data model for the inventory table. Attribution, copyright Rice University, OpenStax, under CC by 4. 0 license. Notice how the schema, Prisma is configured to read the data source database URL from a dotenv file. In the CNA Next/directory, edit the generated dotenv file and change the database connection string as shown in the code snippet below. Replace username with admin name, password with password, and server name with server name for the CNAinventory PostgreSQL database. Database URL equals PostgreSQL, username %40 server name, password at server name, Postgres, database, Azure, com 5432/CNAinventory. Make a copy of the env file and name it env local, as this is the file that will be copied into the Docker container and used by Prisma. To use Prisma in the Next.js application, the Prisma client must be configured. The Prisma client serves as a query builder tailored to the application data. Query builders are part of the ORM that generate the SQL queries used to perform the database operations for the application. To do this, run the command npx Prisma generate add the Prisma client code to the Next.js application. To do this, create the lib subdirectory and navigate into it. Inside the lib directory, create the file Prisma tsx and add the following code. Import Prisma client from @Prisma/client, const global for Prisma global as unknown as Prisma. Prisma client undefined export const Prisma equals global for Prisma. New Prisma client, log, query, if process, env, nodenv, equals production, global for Prisma. Prisma equals Prisma. Now that the Next.js application is configured to map to the inventory table, the next step is to implement the web service code. The web service code consists of React components that render in a browser. The React component inventory props is an array of data records once fetched from the database. The React component inventory implements how the data is displayed as a web page in the browser. The React component layout adds additional navigation to the web page. In the CNA Next/directory, create and navigate to a directory named Components and add the 2 code files that follow into it. Confirm the Components directory is at the same level as the page's directory that was generated. Create the file inventory, tsx, and add the code that follows. Import React from React, export type inventory props equals id, string name, string quantity, string date, string, const inventory React. FC inventory props greater or equal, inventory equals, return div class name equals, flex bg white shadow lg rounded lg mx2 md. mx auto mb5 max w2 xl, div class name equals, flex item start px4 pi3, div class name equals. Div class name equals inline item center justify between, p class name equals text gray 700 text sm, strong id. Inventory id slash strong name, inventory name, quantity, inventory quantity, slash p small class name equals textred 700 text sm date, inventory date to string. Substring 0, 10, slash small slash div slash div slash div slash div slash div, export default inventory, create the file layout, tsx and add the following code. Import React node from React. Import head from next head, type props equals children, React node, const layout, React, fc props equals div class name equals w full text center bgred 800 flex wrap item center, div class name equals text 3 xlw12 text white mx2 md. mx autopy 5 inventory data slash div class name equals layout props, children slash div style JSX global, HTML box sizing, border box, asterisk, before asterisk. After box sizing, inherit, body margin 0, padding 0, font size 16px, font family, Apple System Blink Mac System font, Sego UI Roboto Helvetica Arial Sans Serif, Apple Color Emoji, Sego UI Emoji, Sego UI Symbol. Background RGBA 0000, 5, input Texteria font size 16px, button cursor pointer, slash style JSX, layout padding 02 rem, slash style slash div. Export default layout, edit the index, TSX file and replace the default code with the following code. Declare global namespace node.js, interface global Prisma, any, import Prisma from lib/Prisma. Import inventory props from components inventory, import layout from components layout, export const get server-side props equals async, equals const inventory x equals await Prisma. Inventory, find many, return props, inventoryx JSON, parse JSON, stringify inventoryx, type props equals inventoryx, inventory props index, tsx const inventory feed. React fc props equals return layout div class name equals page br/main props inventoryx map inventoryx equals div key equals inventoryx. id class name equals post, inventory equals inventoryx, /div/main/div style JSX, post, hover box shadow, 1px 3px AAA, post plus. Post margin top, 2 rem, /style/layout, export default inventory feed build, and store microservices images in an Azure Container Registry. Now that the 2 microservices for the cloud-native application have been successfully created, the next step is to create an Azure Container Registry, ACR, to store Docker images for these microservices. Each microservice of the cloud-native application is containerized. Their images are pulled from the ACR and deployed in a Kubernetes environment hosted in the cloud. Create the Azure Container Registry in the Azure portal. On the home page, click on Create a Resource. Click Container Registry. On the Basics tab, configure the resource attributes. Table 12. 2 shows the list of settings to configure on the Basics tab. Any settings not included should be set to the default values provided in the wizard. Basics tab settings subscription, select the default subscription. Resource group for this example, rgnative ipsistis is used. Registry name, enter a unique name for the resource. For this example, ncarregistriflex is used. Location for this example, select the region that is used for the resource group. SKU select standard. Table 12. 2 configuration for the Azure Container Registry. Click Review plus Create. Make a note of the registry name and resource group as these will be needed in a later step. Click Create. When the provisioning is completed, a status message appears. Click on Go to Resource. Make a note of the registry name that was provided in the Create wizard. In this example, the registry name is ncarregistriflex. Generate access keys for the container registry, which will be needed later. For this example, the container registry used is ncarregistriflex. In the Azure portal, navigate to the container registry resource. From the menu on the left, under Settings, click Access Keys. Enable Admin User. Build the Docker images. Now that the container registry has been successfully created, the next step is to build Docker images for each microservice. These images are then pushed to the container registry. Setting specific environment variables makes it easier to run the commands that follow. In the Azure Cloud Shell, run the following commands to set the required environment variables. Note the resource group name in this example is rgnative ipsistis. The registry name in this example is encaregistriflex. Resource group equals resource group name, registry name equals registry name. Containerize the backend service to containerize the backend service. A Docker file must be created with a list of instructions to build the Docker image. Navigate to the kin node express directory. Create a Docker file and add the instructions below. The Docker file starts with a base image for node indicated by the from instruction. A working directory is created and the package. JSON file is copied into it. The dependencies listed in the package. JSON file are used to install the dependent packages. Next, the source code for the Express.js application is copied. Port 8080 is exposed for the Express.js application listens on. Finally, the command to start the Express.js application server is added as the last instruction from node. 14 alpine hash create app directory wrkdir src hash copy package, JSON and package lock, JSON copy package asterisk, JSON/src/hash install npm dependencies, env node env equals production run npm ci only equals production hash bundle app source copy. /src expose 8080 cmd node index JS build the Docker image and push it to the ACR registry. The Docker image must be built locally and then pushed to the ACR registry later. This is assumed a Docker engine is installed on the local computer. To build the image, run the command below. Notice the command has a space followed by a at the end. This references the current directory and must be part of the command. Wait until the Docker image build is complete. Docker build t express image. Test run the backend application by running the Docker container. Run the following command. Docker run dname express image p8080. 8080 express image. Latest open a browser and enter the URL http 127.0.0.1 inventory 1. A screenshot shows the following inventory. id 1 name, yogurt, quantity, 200 date, 2024-0226, attribution, copyright Rice University, OpenStax under CC by 4. 0 license, tag the image so that it can be pushed to the ACR registry with the command below. Note, run Docker images to confirm the correct image name is used for the Docker tagging. Substitute registry name with the correct name of the ACR registry. Docker tag express image, latest registry name, Azure eo/express image. v1 containerize the frontend service to containerize the frontend service. A Docker file must also be created with a list of instructions to build the Docker image. Navigate to the kin next directory, create the Docker file and add the instructions below. The Docker file starts with a base image for node indicated by the from instruction. A working directory is created and the package. JSON file is copied into it. The dependencies listed in the package. JSON file are used to install the dependent packages. Next, the source code for the next JS application is copied. The Prisma client is generated. Port 3000 is exposed because the next JS application listens on port 3000. Finally, the command to start the next JS application server is added as the last instruction from node. LTS busterslim as base run apt, get update in an apt, get install libsl, devca certificates, ywrkdir app copy package, JSON package, lock, JSON. From base as build run export node env equals, production run yarn copy. Run npx prisma generate run yarn build from base as prod, build run yarn install, production copy prisma run npx prisma generate run cp, r node modules prod node modules from base as prod copy, from equals prod, build app prod node modules copy, from equals build app. Next app next copy, from equals build app public copy, from equals build app slash prisma expose 3000 cmd, yarn, start, create the Docker compose. Iml file and add the content below. This step is required so that the env local file is properly copied into the Docker container. Services, web ports, 3000 build, Dockerfile context. /volumes, env, local, app env, local build the Docker image and push it to the ACR registry with this command. The Docker image must be built locally and then pushed to the ACR registry later. To build the image, run the command below. The command will build the image and then run the container. Wait until the image builds and the container starts. Docker compose up D to stop the container. Run the command docker compose down. Test run the front-end application. Because Docker Compose was used for the front end, the Docker container is already running. Open a browser and enter the URL http 127.0.0.1.3000. A screenshot shows the following: inventory data, ID, 1 name, yogurt quantity, 200, date, 2020-40226, ID, 2 name, milk quantity, 100, date, 2020-40226. Rendered using Docker, attribution, copyright Rice University, OpenStax, under CC by 40 license. Tag the image so that it can be pushed to the ACR registry with the command below. Note: run Docker images to confirm the correct image name is used for the Docker tagging. Substitute registry name with the correct name of the ACR registry. Docker tag CNA Next Web, latest registry name, AzureCur. EO/CNA Next Web, v1 push images to ACR registry. First, confirm the images for both the front-end and back-end applications are tagged properly. Run the command, Docker images. The following 4 images should be listed, the originally built images, and then the images tagged for the ACR registry. A screenshot shows the list of Docker images with tag, image ID, CREATED size. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Log in to the ACR registry with the command below. As Acker login name registryname note. Running the above command assumes being logged into the Azure portal. This can be done with the following Azure CLI command: as login scope https management core Windows net. Default push both images to the ACR registry. Run the 2 commands below. Substitute registry name with the correct name of the ACR registry. Docker push registry name, AzureCur, EO/ExpressImage. v1 Docker push registry name, AzureCur, EO/CNA Next Web, v1 in the Azure console. Navigate to the container registry and click on the registry name, ncaregistriflex. Under Services, click Repositories. Confirm that both image repositories are created. For this example, the repositories are ExpressImage and CNA Next Web. Create an Azure Kubernetes service instance now that the Docker images for the 2 microservices have been created and pushed to their respective repositories. The next step is to create a Kubernetes cluster. In the Azure portal search bar, search for Kubernetes services. Click on Kubernetes services. Select Create a Kubernetes cluster. On the Azure portal homepage, click on Create a resource. From the menu on the left, click Containers. Click on Azure Kubernetes Service, AKS. On the Basics tab, configure the resource attributes. Table 12.3 shows the list of settings to configure on the Basics tab. Any settings not included should be set to the default values provided in the wizard. Basics tab settings subscription, select the default subscription. Resource group, for this example, RG native Ipsistis is used. Kubernetes cluster name, enter a unique name for the resource. For this example, NCAX is used. Scale method, select manual. Location, for this example, select the region that is used for the resource group. Node count set to 2. Table 12.3 configuration for the Azure Kubernetes service. On the Integrations tab, select the container registry that was created previously. Click Review plus Create, then click Create. Wait until the Kubernetes cluster is provisioned. Deploy microservices to the Kubernetes cluster. Now that the Kubernetes cluster is provisioned successfully, the next step is to deploy the containerized microservices into it. The images for these microservices are pulled from the registry and deployed into pods in the Kubernetes cluster. Set up the environment setting specific environment variables makes it easier to run the commands that follow. Environment variables need to be set up for the resource group, Kubernetes cluster, and the container registry. Run the following commands to set these variables. Note that for this example, the resource group used is RG native Ipsistis, the Kubernetes cluster name used is NCAX, and the registry name is ncaregistry. Resource group equals resource group, cluster name equals cluster name, registry name equals registry name. The Kubernetes cluster must be able to connect to the ACR registry to pull the Docker images from it. Connect the Kubernetes cluster to the ACR registry using this command. As ax get credentials resource group, resorcgup name clustrnme kubectl is the Kubernetes command line tool that is used to manage Kubernetes clusters. This is the tool that interacts with the Kubernetes cluster on Azure. The first step in interacting with the Kubernetes cluster is to connect to it. Run the command, which lists the nodes of the Kubernetes cluster. The output lists the nodes for the cluster. Kubectl get nodes. The next step is to obtain the hostname to the ACR registry. This is added to the deployment manifest files for the microservices so that the Docker images can be pulled from the registry and deployed into the Kubernetes cluster. Run the command to query the ACR server. As acker list resource group resourcgroup query, acker login server, output table create, and apply the deployment manifests. Deployment manifest files are used to deploy the Docker images for the microservices into the Kubernetes cluster. They provide declarative updates for the Kubernetes pods and replica sets for the microservices. Initially, only one instance of each microservice is made available. Each microservice can scale up or down as needed. Create a deployment manifest file for the Docker image, express image for the backend service. Create the express deployment, YAML file, and enter the following content. The deployment manifest deploys the backend service with the label CNA Express. In this deployment manifest file, the Docker image is pulled from the registry and gets deployed in a pod in Kubernetes. Hash deployment. YAML API version, apps v1 kind, deployment metadata, name, CNA Express spec, selector, hash define the wrapping strategy match labels, hash match all pods with the defined labels app. CNA Express hash labels follow the name, value template, hash this is the template of the pod inside the deployment metadata, labels, app, CNA Express spec, containers, image, encregistry, AzureCur. EO/express image name, express image ports, container port, 80 apply the deployment manifest to the Kubernetes cluster with the following command. A message indicates that the deployment object was successfully created. Kubectl apply F, express deployment. YAML create a deployment manifest file for the Docker image, web image for the front-end service. Create the web deployment, YAML file, and enter the following content. The deployment manifest deploys the front-end service with the label CNA web. In this deployment manifest file, the Docker image is pulled from the registry and gets deployed in a pod in Kubernetes. Hash deployment. YAML API version, apps v1 kind, deployment metadata, name, CNA web spec, selector, hash define the wrapping strategy match labels, hash match all pods with the defined labels app. CNA web hash labels follow the name, value template, hash this is the template of the pod inside the deployment metadata, labels, app, CNA web spec, containers, image, encregistry, AzureCur, EO/web image name. Web image ports, container port, 80 apply the deployment manifest to the Kubernetes cluster with this command. A message indicates that the deployment object was successfully created. Kubectl apply F, web deployment. YAML confirm the deployments for both the backend and front-end services were successful with the following commands. Both microservices should display a status of running in the Kubernetes cluster. Kubectl get deploy CNA Express. Kubectl get pods in the Azure console. Navigate to the Kubernetes resources page. Click on workloads. The microservices are deployed with a status of ready. A screenshot shows that both microservices are successfully deployed and running in the Kubernetes cluster from the Azure console. Used with permission from Microsoft, create and apply the service manifests. Both microservices are now deployed in a Kubernetes cluster. Kubernetes services are created for each microservice so that they can receive client requests. Kubernetes provides the pods where the microservices are deployed with IP addresses and a single fully qualified domain name, FQDN, for a set of pods. In addition, services expose TCP ports to the containers where the microservices are running. Create a service manifest file for the Docker image, express image for the backend service. Create the express service. YAML file and enter the following content. The service manifest creates the Kubernetes service for the backend service with the label CNA Express. Service, YAML API version, v1 kind, service metadata, name. CNA Express spec, type, cluster IP selector, app, CNA Express ports, port, 8080 hash service exposed port name, HTTP hash service port name protocol. TCP hash the protocol the service will listen to target port. 8080 apply the service manifest to the Kubernetes cluster with this command. A message indicates that the service object was successfully created. Kubectl apply F, express service. YAML create a service manifest file for the Docker image, web image for the front-end service. Create the web service. YAML file and enter the following content. The service manifest creates the Kubernetes service for the front-end web service with the label CNA web. Service. YAML API version, v1 kind, service metadata, name, CNA web spec, type, cluster IP selector. App CNA web ports, port, 3000 hash service exposed port name, HTTP hash service port name protocol, TCP hash the protocol the service will listen to target port. 3000 apply the service manifest to the Kubernetes cluster with this command. A message indicates that the service object was successfully created. Kubectl apply F, web service. YAML confirm the service deployment was successful. The services for each microservice should be listed. IP addresses, cluster IP, and ports should also be specified for each microservice. Kubectl get service CNA express Kubectl, get service create, and apply the ingress controllers now that the services are created with assigned IP addresses and exposed ports. Ingress controllers are used to define how the deployed microservices are exposed to outside requests. First, enable the Kubernetes cluster so that it can use HTTP application routing with the following command. ASAX enable add-ons resource group, /name CLUSTRNAME add-ons HTTP application routing next, configure and deploy the ingress controller. As mentioned earlier, an FQDN is provided for a set of pods of the Kubernetes cluster. Run this command to obtain this FQDN. The output is the FQDN that is used to expose the microservices to outside requests. ASAX show resource group RESORCGRUP name CLUSTRNAME OTSV /query add-on profiles, HTTP application routing, config, HTTP application routing zone name create the ingress descriptor file, express ingress. YAML for the backend service labeled as CNA Express and add the following content. Note that the host includes the FQDN that was obtained in the previous step. It is prepended with CNA Express making it unique for the backend service. Hash ingress, YAML API version, networking, K8s, IOV1 kind, ingress metadata, name, CNA Express annotations, Kubernetes. IO ingress, class, add-on HTTP application routing spec, rules, host, CNA Express, 8776 BB 8BC0324 E10946C. Eastus, ACCEP, IO HTTP, paths, path, hash which path is this rule referring to path type, prefix backend, hash how the ingress will handle the request service, name. CNA Express hash which service the request will be forwarded to port, name. HTTP hash which port in that service, apply the ingress manifest to the Kubernetes cluster with this command. A message indicates that the ingress object was successfully created. Kubectl apply F, express ingress. YAML create the ingress descriptor file, web ingress. YAML for the front-end web service, labeled as CNA web, and add the following content. Note that the host includes the FQDN that was obtained in the previous step. It is prepended with CNA web making it unique for the front-end web service. Hash ingress, YAML API version, networking, K8s, IOV1 kind, ingress metadata, name, CNA web annotations, Kubernetes. IO ingress, class, add-on HTTP application routing spec, rules, host, CNA web, 8776 BB 8BC0324 E10946C. Eastus, ACCEP, IO HTTP, paths, path, hash which path is this rule referring to path type, prefix backend, hash how the ingress will handle the request service, name. CNA Express hash which service the request will be forwarded to port, name. HTTP hash which port in that service, apply the ingress manifest to the Kubernetes cluster with this command. A message indicates that the ingress object was successfully created. Kubectl apply F, web ingress. YAML confirm the ingresses were deployed successfully with the commands below. The ingresses for both microservices will display host names, HOSTS, that are unique for each microservice. Kubectl get ingress CNA Express Kubectl, get ingress the command below queries Azure for the FQDN that was created earlier. It serves as the zone name. The command also returns the resource group value that is used to access the microservices. Run the command below and make a note of the zone name and resource group values. As network DNS zone list output table substitute the values for resource group and zone name obtained in the previous step for resource group and zone name, respectively, in the command that follows. Execute the edited command in the Cloud Shell, which results in the table shown. 2 records are added for CNA Express and 2 for CNA Web, which show in the name column. As network DNS record set list G resource group Z zone name, output table a screenshot a list under the following categories TTL, FQDN, name, provisioning state, resource group. Attribution. Copyright Rice University, OpenStax, under CC by 40 license, in a browser, access the backend service using the URL that is generated, e.g., http://CNA Express. 8776 BB8 BC0324 E10946C Eastus AXAP IO Inventory 1, which includes the route that was implemented as part of the REST API for the microservice. The backend service receives requests in JSON format to create and store inventory records into the data store. It also retrieves inventory records from the data store and renders them in JSON format. A screenshot shows the following: inventory, id, 1 name, yogurt, quantity, 200, date, 2023-04-17, attribution. Copyright Rice University, OpenStax, under CC by 40 license, in a browser. Access the front-end web service using the URL that is generated, e.g., http://CNA web. 8776 BB8 BC0324 E10946C Eastus AXAP IO. The front-end web service renders inventory records from the data store to a web page. A screenshot shows the following: inventory data, ID, 1 name yogurt quantity, 200, ID, 2 name milk quantity, 100, rendered using Kubernetes, attribution. Copyright Rice University, OpenStax, under CC by 40 license. PA-S deployment of a sample cloud-native application using VMware Tanzu. This section demonstrates how to use VMware Tanzu deployment technology to launch a dashboard on Oz monitoring application metrics exposed by the keyword Kubernetes up and running demo application. Amazon Web Service, AWS, is an Amazon cloud computing platform that offers a wide range of services that allow customers to build, deploy, and manage applications and services in the cloud, and will be used in this example. Set up an environment for VMware Tanzu. The first step is to create an Oz EC2 instance. This is a VM hosted in the cloud. Once the EC2 instance is provisioned, a set of tools need to be installed, including Docker, Kubernetes CLI tool, and other relevant package managers. Create the EC2 instance. AWS Portal is a web-based console that allows customers to manage their cloud services and Oz subscriptions. In the AWS Portal, search for EC2 and click Launch Instance. Amazon Elastic Compute Cloud, EC2, is a cloud-based, on-demand compute platform that can be auto-scaled to meet demand. Under Application and OS Images, Amazon Machine Image, select Ubuntu and leave the remaining configurations to the default settings for this section. Under the Instance Type section, select T2, Micro for the instance type. Under the Key Pair Login section, click on Create New Key Pair. Enter a value for key pair name and keep the default settings. Click on Create Key Pair. The name used for this example is CNA Tanzu Private Key. Download the CNA Tanzu Private Key (PEM) file. This file is used to log in to the EC2 instance. The name provided, CNA Tanzu Private Key, is populated for the key pair name in the Key Pair Login section. Under the Networking Settings section, select Create Security Group. Enable Allow SSH traffic from, allow HTTPS traffic from the Internet, allow HTTP traffic from the Internet. Set anywhere to 00. 000. Under the Summary section, click Launch Instance. Wait until the provisioning is complete. A success message appears with the instance ID. Click on the instance ID link. Open a terminal and navigate to the directory where the CNA Tanzu Private Key (PEM) file was downloaded. Under Instance Summary, copy the value from public IP4 DNS. Use the command to make an SSH connection to the EC2 instance by inserting the copied public IP4 DNS. SSH inukem private key. PEM Ubuntu at EC2 public IP4 DNS. Install Homebrew. Homebrew is an open-source package management system used to install and manage packages on macOS and Linux operating systems. Homebrew, also referred to as Brew, is used to install Octant later. Homebrew uses a compiler environment to build packages that may need to be built. The first step is to install a compiler environment with this command. The package Build Essentials provides all required packages for the compiler environment. Run the command below to install the Build Essentials package sudo apt install build essential. Run the following command to download the Brew installation script that is used to install Brew. Curl fssl-o install. Sh run the following command to launch the installation script. Bin bash install. Sh once the installation script is complete, run the following two commands to add Brew to the path environment variable. This makes the command Brew recognizable in the EC2 instance. Echo eval $$/home/linuxbrew/bin/brew shellenv /home Ubuntu. Profile eval $/home/Linux brew/bin/brew shellenv. Confirm brew was added to the path environment variable. Type the command brew to confirm the brew help menu is printed to the console. This indicates that brew was installed successfully. Install and set up Docker Tanzu requires the Docker engine to be up and running. Docker Engine is an open-source containerization platform used to build Docker images and manage Docker containers. To install the Docker Engine, Advanced Package Tool, apt, is used. Apt is a packaging tool used to install new packages and update existing packages. Run the command to update the apt utility itself before installing Docker. Sudo apt update. Run the command below to install the following packages as prerequisites for installing Docker. apt transport HTTPS, which allows the package manager to transfer files over the HTTPS protocol certificates, which makes available common certificate authority certificates to aid in verifying the security of connections curl, which is used for transferring data to or from a server software properties common, which is a package to help manage the software installations. Sudo apt install apt transport HTTPS certificates curl software properties common. Download a public key file from Docker with the command below. The public key file is then added to a list of trusted keys managed by apt curl fssl https. Download docker com/linux/ubuntu/gpg sudo apt-key. Add run the adapt repository command below to add the external Docker repository to the apt sources list. Sudo adapt repository /deb arch equals amd64 https. Download docker linux ubuntu bionic stable sudo adapt repository deb arch equals amd64 https. Download docker linux ubuntu bionic stable. After making the changes to the apt package information in the previous steps, update the apt index with this command. Sudo apt update. Run the command below to install Docker on the EC2 instance. Sudo apt install docker c. Run the next three commands to configure Docker and install Docker Compose. Add the current Ubuntu user to the Docker group. Sudo usermod ag docker user download Docker Compose. Docker Compose is a tool used for defining, via descriptor files, and managing applications that consist of multiple Docker containers. Sudo curl /https github com Docker Compose releases download 129 2/Docker Compose $uname s $uname m /o/usr/local/bin/Docker Compose. Run this command to change the permissions of the downloaded Docker Compose file to an executable so that it can be run. Sudo chmod plus x usr/local/bin/Docker Compose. Confirm that both Docker and Docker Compose were installed. Run these commands and confirm that the versions for Docker and Docker Compose are displayed to the console. Docker v Docker Compose v. Run the command below to start the Docker engine in the EC2 instance. Sudo systemctl start Docker. Run the command below to test if Docker was installed correctly. Sudo docker run hello world install and set up kubectl tanzu requires kubectl. The Kubernetes command line tool, kubectl, is used to interact with the Tanzu Kubernetes cluster. Download the latest release of kubectl with the command below. curl /https//dl k8s eo/release/$ curl ls /https//dl k8s io release stable txt/bin/linux/amd64/kubectl. Install kubectl with the command below. Sudo install root groot m755 kubectl/usr/local/bin/kubectl. Run the following commands to change the permissions to kubectl file to executable so that it can be run and copy it to the local bin directory chmod plus x kubectl mkdir p local bin mv /kubectl local/bin/kubectl append local bin to the path environment variable. Edit the bashrc file and add the following line to the end of it. Export path equals $path, local bin save and close the file. Apply the changes by running the following command. Source, bashrc confirm, by running the command kubectl that it can be executed. The kubectl help menu should display in the console. This indicates that it was installed successfully. Install Tanzu install JQ as a support package for Tanzu with the following commands. Sudo apt-get update sudo apt-get install JQ install xdgutils as a support package for Tanzu with the following command. Sudo apt-get install reinstall xdgutils ensure the kubectl version is compatible with the Tanzu version. curl h backslash accept, application slash vnd, GitHub, v3, raw l backslash https, slash API, GitHub, com/repos VMware Tanzu /community edition /content /hack /get release, sh /bash sv0, 10. 0 Linux. Unpack the gzip file and install Tanzu using the provided shell script with the command below. tar xcvf tc linux amd 64v0, 10.0, tar. gz navigate into the tc linux amd 64v0, 10.0 directory and run the installation shell script with the command below. Install. sh confirm Tanzu was installed successfully. Run the command Tanzu. The Tanzu help menu should be displayed in the console. Install and test the Qword demo application now that the Docker engine, Docker Compose, kubectl, and Tanzu are all installed. The next step is to install the Qword demo application. Create required AWS secret and access keys. AWS secret keys are used to manage Oz resources via the AWS CLI. Oz CLI is a command line interface used to manage Amazon Cloud Services. Access keys are used in the Tanzu configuration to provision and configure the Tanzu management cluster. An RSA key pair is also used in the Tanzu configuration to communicate with the Tanzu management cluster. In the AWS shell, install Oskli. First, download the AWS CLI zip file with the curl command below. Curl https://oskli, Amazonos, com/oskli xlinux x8664, zip, o oskliv2, zip, install the unzip CLI utility that is used to unpack the downloaded oskliv2 zip file. Run the command below, sudo apt install unzip the oskliv2 zip file with the command below, unzip oskliv2 zip, install the unpackaged AWS CLI with the command below, sudo oz install. Run the command below to verify that the AWS CLI was installed successfully. The version should be displayed. Oz version in the AWS portal under Access Management. Click on Security Credentials. Click on Create Access Key to generate the key. Make a note of the key pairs as they will be added to the Tanzu Management Cluster settings. Finally, generate an RSA key pair. The name used in this example is Tanzu key pair. Make a note of the name of the RSA key pair as it will be added to the Tanzu Management Cluster settings. Oz ec2 create key pair /key name Tanzu key pair /key type RSA /key format pem /query key material /output text Tanzu key pair. Pem create the Tanzu Management Cluster configuration. Now that the environment to run the Tanzu Management Cluster is set up, the next step is to create a Tanzu Management Cluster. A management cluster configuration file is needed. One way to create a management cluster configuration file is to use the Tanzu installer, which is a web page that is used to generate the configuration file. 14. Use the Tanzu installer to create the management cluster configuration file. Launch the Tanzu installer web page with the command below. A browser page automatically launches. Tanzu Management Cluster. Create a screenshot shows a Tanzu installer. Credit Tanzu under Mozilla Public License 2. Select Deploy on Amazon Web Services. This generates a configuration file that deploys the cluster on the Amazon EC2 instance that was created earlier. Under the IaaS provider section, select the region that is also used as a location for the EC2 instance. Under the Management Cluster Settings section, make sure that Bastion Host is unchecked, disabled. For EC2 key pair, enter the name of the RSA key pair that was created earlier. For this example, the name used in this example is Tanzu key pair. Select T3A large for the AZ1 worker node instance type. Under the Identity Management section, disable Enable Identity Management settings. Under the OS image section, select Ubuntu 20-0 4AMD64 as the OS image. Click Review Configuration. Table 12. 4 shows the complete list of settings expected for configuring the Tanzu Management Cluster. IaaS Provider Settings. IaaS Provider validate the Oz Provider credentials for Tanzu Community Edition. AWS Credential Profile Default Regionus East 2 VPC for Oz Settings VPC. For Oz Specify VPC Settings. For Oz VPC CIDR 10. 0016 Management Cluster Settings. Management Cluster Settings Development Cluster selected. 1 Node Control Plane DEV Instance Type T3A. Large Management Cluster Name TKG CNAM Cluster ROS EC2 Key Pair Tanzu Key Pair. Enable Machine Health Checks. Yes. Enable Bastion Host. No. Enable Audit Logging. No. Automate Creation of AWS CLOUD format. Stack Yes Availability Zone 1S East 2C Worker Node, Instance Type 1T3A. Large prod instance type metadata settings, metadata specify metadata for the management cluster location, optional, description, optional, labels Kubernetes network settings, Kubernetes network cluster pod CIDR. 196.0.0.11 CNI provider and TRIA cluster service CIDR 100.64.0.0.13 cluster pod CIDR 100.96.0.0.11 enable proxy settings, no identity management, settings identity management specify identity management, enable identity management settings, no OS image settings, OS image OS image. Ubuntu 20.04 AMD 64, AMI 06159 FTD 27, 11 F3434, OS image Ubuntu 20.04 AMD 64, AMI 06159 FTD 27, 11 F3434, Table 12. For configurations for Tanzu, copy the generated CLI command to the clipboard or click Deploy Management Cluster. Clicking on the Deploy Management Cluster button connects to the EC2 instance and provisions the Tanzu Management Cluster. Alternatively, the configuration file that was generated is copied into the home Ubuntu config /tanzu/tkg/clusterconfigs/ directory. In this example, the generated file name for the configuration file is kldlarkil. YAML, run the copied command in the Oz shell to provision the Tanzu management cluster. After the copied command is executed, a config file with config, prepended as the file name, is generated and copied into the kubekg/tmp/ directory. Run the command below to check the status of the Tanzu management cluster. Change config file with the file name generated, kubectl get \po, deploy, cluster. Kubeden control plane machine deployment / a kubeconfig home ubuntu kubekg/tmp/config file. A screenshot shows numerous items in a list under the following categories: NAMESPACE, name, ready, status, restarts, age. Attribution, copyright Rice University, OpenStax under CC by 40 license. Run the QARD demo application. QARD, Kubernetes Up and Running Demo, is a demo application that provides information about Kubernetes environments that are running. The QARD demo application is deployed in the Tanzu management cluster as a containerized application. Run the command below to set the default context to the Tanzu cluster that was just created. Kubectl config use context tkg cnam cluster RAS admin at tkg cnam cluster RAS. Run the command below to pull the QARD image and start a single instance of a QARD pod. Kubectl run restart equals never image equals gcr. eo/qardemo/qardamd64. Blue QARD configure QARD to listen on port 8080 and forward to port 8080 in the QARD pod. First, run the command below to list the pod and make note of the pod name. The pod name should be QARD and should be up and running. Kubectl get pods run the command below to use port forwarding and expose the QARD default port, 8080. Kubectl port forward QARD 8080. 8080 launch the QARD website in the browser using the URL http localhost 8080. A screenshot shows the QARD website. Credit. Kubernetes under Mozilla Public License 2, install and run Octant. Octant is an open-source web interface for Kubernetes that is used to inspect Kubernetes clusters and applications deployed in them. Run the command below to install Octant using Homebrew. Brew install Octant launch Octant by typing the command Octant in the AWS shell. A browser window automatically launches. A screenshot shows the Octant website. Credit, Octant, a VMware-backed project. FAS deployment of a sample cloud-native application. The following example 15 illustrates FAS deployment of a cloud-native application that consists of two event-driven workloads. The first serves as a simulator that sends data to an event hub. This is the Azure FAS producer function. A second connects to this event hub to trigger storing the events in a data store. This is the Azure FAS consumer function. Both FAS functions are deployed as Azure Function Apps. Azure Function App is an event-driven serverless compute platform without provision or managing infrastructure. The data store used is an Azure Cosmos database. Dashboards are then used to monitor the performance of the Azure FAS functions. The architecture of the FAS deployment of the cloud-native application is shown in Figure 12.40. A diagram shows the following flow. FAS producer function, event bus FAS consumer function, Azure Cosmos DB, Figure 12. 40 FA-S functions of a cloud-native application are deployed in Azure. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. FA-S environment setup setting specific environment variables makes it easier to run these commands. Run the commands below to set the environment variables. For this example, rgata functions westus2 was used for the resource group. Encafa7thub was used for the event hub namespace. Encafa7thub was used for the event hub name. Encafasoth was used for the event hub authorization rule. Encafosbusser was used for the Cosmos database account username. Encafoster was used for the storage account name. Encafosapp was used for the FA-S function name for the first Azure function, and westus2 was used for the location. Resource group equals value. Event hub namespace equals value event hub name equals value event hub authorization rule equals value Cosmos DB account equals value. Storage account equals value function app equals value. Location equals value. Create a data store for the event-driven FA-S cloud-native application. The producer function simulates and sends data to an Azure Event Hub. The consumer function listens for events of a specific namespace in the Azure Event Hub and processes and stores them in an Azure Cosmos database. The first step is to create an Azure Cosmos DB data store. Once the data store is created, the next step is to create and configure an Azure Event Hub. Run the commands below to create the Azure Cosmos DB data store. As Cosmos DB create /resource group /name Cosmos DB account $. As Cosmos DB SQL database, create /resource group /account name Cosmos DB account $, /name telemetry. DB as Cosmos DB SQL container create /resource group /account name Cosmos DB account /database name telemetry DB name telemetry info /partition key path temperature status create. And configure an Event Hub. Run the commands below to create the Event Hub namespace. Azure Event Hub and Event Hub authentication rule resources. As Event Hub's namespace, create /resource group /name Event Hub NMESPACE. As Event Hub create /resource group /name Event Hub name /namespace name Event Hub namespace /message attention. 1. As Event Hub authorization rule create /resource group $name Event Hub authorization rule Event Hub name $namespace name Event Hub NAMESPACE /rights. Listen send run these commands below to create the storage account and function app resources. As storage account create /resource group /name storage account p /scu standard LRS as function app create /resource group /name function app p /storage account p /consumption plan location /runtime Java /functions version 4 create. Build and deploy the FA-S producer function. A few resources need to be created for the FA-S producer function. First, a storage account is created. The FA-S producer function needs to connect to the Azure Event Hub. Connection strings need to be generated for this purpose. Finally, the FA-S producer function is built as a Maven project and then deployed as an Azure Function app. Set up storage for the consumer function. Run the commands below to create the connection strings that are used to access the storage account for the Event Hub. Azure Web Jobs storage equals $as storage account show connection string /resource group /name storage account p /query connection string /output tsv Event Hub connection string equals $as Event Hub authorization rule keys list /resource group /name Event Hub authorization rule /Event Hub name namespace name Event Hub namespace /query. Primary connection string /output tsv. Run the commands below to obtain the connection strings that were created in the previous step. Make a note of these connection strings as they will be used later. Echo Azure Web Jobs storage. Echo Event Hub connection string. The connection strings that were generated for the Azure Web Jobs storage and Event Hub in the previous step need to be added as application settings to the Azure Function app account in the command. Run the command below with these values inserted to create the function app. A notification to the console indicates that the function app was built successfully. As function app config app settings, set /resource group /name function app p /settings /Azure Web Jobs storage equals $Azure Web Jobs storage /Event Hub connection string equals $Event Hub connection string build and deploy the FA-S producer function now that the Azure resources, such as the Event Hub, Azure Function app, and storage account, have been created and configured. The next step is to create an Azure FA-S function project for the FA-S producer function. Maven is used to build the project. Run the command below to create and build the function project. The telemetry function's producer directory is generated along with the files for the project. A build success message indicating the build was successful should appear in the console. MVN archetype, generate batch mode /darchetype grouped equals com, Microsoft. Azure /darchetype artifact ID equals Azure functions archetype /dap name equals $function app p /resource group equals $resource group /dap region equals $location /dap service plan name equals $location plan /dgrouped equals com. Learn /dartifact ID equals telemetry functions producer. Run the command below to add application settings from the Azure function into the function project local. Settings. JSON file located in the telemetry functions producer root directory. Func Azure function app fetch app settings function app p. Navigate to the telemetry functions producer /src /main /java /com /learn /directory. Edit the function Java file and replace all the code in it with the code that follows. The code declares a function that establishes a connection to the Azure Event Hub, package com, learn, import com, Microsoft, Azure, functions, annotation. Event Hub output import com, Microsoft, Azure, functions, annotation, function name, import com, Microsoft, Azure, functions, annotation, timer trigger, import com, Microsoft, Azure, functions, execution context. Public class function at function name generates sensor data. At Event Hub output, name equals event hub name equals blank because the value is included in the connection string connection equals Event Hub connection string. Public telemetraltum generate sensor data. At timer trigger, name timer info. Schedule /10, every 10 seconds string timer info. Final execution context. Get logger info Java timer trigger function executed at plus Java, time, local date time. Now, double temperature equals math random, 100, double pressure equals math random, 50. Return new telemetraltum, temperature, pressure. Create a file named telemetry item, Java, and add the code below. The code declares simulated data items that are pushed to the Azure Event Hub, package com, learn. Public class telemetry item, private string id, private double temperature, private double pressure, private boolean is normal pressure, private status temperature status. Static enum status, cool, warm, hot, public telemetry item, double temperature, double pressure. This, temperature equals temperature, this, pressure equals pressure. Public string getid, return id. Public double get temperature, return temperature. Public double get pressure, return pressure. At override public string to string, return telemetry item equals, ID equals plus id plus, temperature equals plus temperature plus, pressure equals plus pressure plus. Public boolean is normal pressure, return is normal pressure. Public void set normal pressure boolean is normal. This is normal pressure equals is normal. Public status get temperature status, return temperature status. Public void set temperature status, status temperature status. This temperature status equals temperature status. In the telemetry functions producer directory, run the command below to build the function. A build success message appears in the console indicating the build was successful. MVN clean package. Run the command below to test the function and confirm it runs properly. The output shown indicates the function is running properly. MVN Azure Functions. Run. A screenshot shows text below Azure Functions core tools. Attribution. Copyright Rice University, OpenStax, under CC by 40 license. Run the command below to deploy the FA-S producer function as an Azure function app. Once the deployment is complete, the HTTP trigger URLs are provided. MVN Azure Functions, deploy. Create, build, and deploy the FA-S consumer function. Now that the FA-S producer function is built and deployed, the next step is to create an Azure FA-S function project for the FA-S consumer function. Like the FA-S producer function, a few resources need to be created for the FA-S consumer function. A storage account is created. The FA-S consumer function needs to connect to the Azure Event Hub. The FA-S consumer function also needs to connect to the Azure Cosmos DB data store. The FA-S consumer function is built as a Maven project and then deployed as an Azure function app. Run the commands below to create a storage account and the FA-S consumer function. As storage account, create /. resource group backslash. Name storage account C backslash. SKU standard LRS. As function app create backslash. Resource group backslash. Name function app C backslash. Storage account C backslash. Consumption plan location backslash. Runtime Java backslash. Functions version 4. Use the commands below to obtain the connection strings for the storage account and the data store. These values, as well as the data store information, are required for the consumer function. Azure Web Jobs Storage. As storage account show connection string backslash. Resource group backslash. Name storage account C backslash. Query connection string backslash. Output TSV. Cosmos DB connection string equals $backslash. As Cosmos DB keys list backslash. Resource group backslash. Name Cosmos DB account backslash. Type connection strings backslash. Query connection string 0. Connection string backslash. Output TSV. Run the command below to obtain the Event Hub connection string. Event Hub connection string. As Event Hub authorization rule keys list backslash. Resource group backslash. Name Event Hub authorization rule backslash. Event Hub name backslash. Namespace name Event Hub namespace backslash. Query primary connection string backslash. Output TSV. Run the commands below to display the connection strings that were created in the previous steps. Make a note of these connection strings as they will be used later. Echo Azure Web Job Storage. Echo Event Hub connection string $. Echo Cosmos DB connection string. The connection strings that were generated for the Azure Web Job Storage, Event Hub, and Azure Cosmos DB data store in the previous step need to be added as application settings to the Azure Function App account in the command. Run the command below with these values inserted to create the function app. A notification to the console indicates that the function app was built successfully. As function app config app settings set backslash. Resource group backslash. Name function app C backslash. Settings backslash. Azure Web Jobs Storage equals $Azure Web Jobs Storage backslash. Event Hub connection string equals $Event Hub connection string backslash. Cosmos DB connection string equals $Cosmos DB connection string. Build and deploy the FAS consumer function. Now that the Azure resources, such as the Event Hub, Azure Function App, Storage Account, and Azure Cosmos DB, have been created and configured, the next step is to create an Azure FAS function project for the FAS producer function. Maven is used to build the project. Run the command below to create the function project for the FAS consumer function. The telemetry function's consumer directory is generated along with the files for the project. MVN archetype, generate batch mode backslash. Darchetype group ID equals com, Microsoft, Azure. Darchetype artifact ID equals Azure Functions Archetype. DAP name function app C backslash. Resource group. DAP region equals $location backslash. DAP service plan name equals $location plan backslash. Day grouped equals com. Learn backslash. Dartifact ID equals telemetry functions consumer. Navigate into the telemetry functions consumer directory. Run the command below to update the local settings for local execution with the command. These settings are added to the local settings JSON file. Func Azure Function App fetch app settings backslash function app p. Navigate to the src/main/java/com/learn/directory. Replace all the code in function Java with the code shown below. The code declares a function that establishes connections to the Azure Event Hub and Azure Cosmos DB. Package com, learn, import com, learn, telemetry item, status. Import com Microsoft, Azure, functions, annotation. Function name, import com Microsoft, Azure, functions, execution context, import com Microsoft, Azure, functions, output binding, import com Microsoft, Azure, functions. Annotation cardinality, import com, Microsoft, Azure, functions, annotation, Cosmos DB output, import com, Microsoft, Azure, functions, annotation, Event Hub trigger. Public class function. At function name, process sensor data. Public void process sensor data. At Event Hub trigger. Name equals MSG. Event hub name equals blank because the value is included in the connection string. Cardinality equals cardinality. 1. Connection equals event hub connection string. Telemetry item item. At Cosmos DB output. Name database output. Database name equals telemetry DB. Collection name equals telemetry info. Connection string setting equals Cosmos DB connection string. Output binding telemetry item document. Final execution context. Get logger info event hub message received plus item to string if item get pressure 30. Item set normal pressure false. Else item set normal pressure true. If item get temperature 40. Item set temperature status cool. Else if item get temperature 90. Item set temperature status hot. Else item set temperature status warm. Document set value item. Create the file telemetry item, Java, and add the code shown below. The code declares data items that are received from the Azure Event Bus and stored in the Azure Cosmos DB data store. Package com, learn. Public class telemetry item. Private string id, private double temperature, private double pressure, private boolean is normal pressure, private status temperature status. Static enum status. Cool, warm, hot. Public telemetry item, double temperature, double pressure. This temperature equals temperature, this pressure equals pressure. Public string get id. Return ids. Public double get temperature. Return temperature. Public double get pressure. Return pressure. At overrides. Public string to string. Return backslash telemetry item equals ID equals plus id plus backslash temperature equals plus temperature plus pressure equals plus pressure plus. Public boolean is normal pressure. Return is normal pressure. Public void set normal pressure. Boolean is normal. This is normal pressure equals is normal. Public status get temperature status. Return temperature status. Public void set temperature status temperature status. This temperature status equals temperature status. Navigate to the telemetry function's consumer directory and build the function with the command below. Once the build is complete, a build success message is displayed to the console to indicate the build was successful. MVN clean package. Run the command below to test if the function runs properly. MVN Azure Functions. Run. As mentioned earlier, the FAS consumer function listens to events of a specific namespace in the Azure Event Hub and processes and stores them in an Azure Cosmos DB data store. The events stored in the Azure Cosmos DB data store can be checked by visiting the Azure Cosmos DB page in the Azure portal. In the Azure portal, navigate to the Azure Cosmos DB page. On the left menu, click on Data Explorer, click on the Telemetry Info tab, and then click on Items expanded from Telemetry Info to view the data. Data will continue to be sent to the Azure Cosmos DB data store, which can be viewed in real time. Run the command below to deploy the functions to Azure Functions. Once the deployment completes, a build success message appears in the console. MVN Azure Functions. Test the deployed FAS producer and consumer functions. Now that both the FAS producer and consumer functions are successfully deployed as Azure Function apps, data continues to be simulated, pushed to the Event Hub, and then stored in the data store. The next step is to test them and evaluate their performance. The FAS producer function continues to send telemetry data to the Azure Event Hub, while the FAS consumer function continues to process events from the Azure Event Hub and store them in the Azure Cosmos DB data store. The activities and performance of these two functions can be viewed in Application Insights in the Azure portal. Evaluate the FAS producer function. The first step is to inspect the application map for both FAS functions. Application maps represent the logical structure of a distributed application. Individual components of the application are identified by their role name property and are independently deployed. These components are represented as circles, called nodes on the map. HTTP calls between nodes are represented as arrows connecting the source node to the target node. Application maps help identify performance bottlenecks or failure hotspots across all components via alerts. The application map, Figure 12.41, displays the logic structure of the FAS producer function in Azure Event Bus. It shows the FA-S producer function as a node connected to an Azure Event Hub, also as a node. The application map for the FA-S producer function shows that there is a dependency between the FA-S producer function and the Azure Event Hub. It also shows the FA-S producer function is not dependent on the FA-S consumer function nor the Azure Cosmos DB data store. A diagram shows the following flow: 1 instance 67. 1 MS210 calls NCAFAs, Azure Event Hubs 1 instance 294, 9 MS12 calls. Figure 12. 41. This application map shows the FA-S producer function as a node connected to an Azure Event Hub, also as a node. Used with permission from Microsoft. The application map shown in Figure 12. 42 displays the logic structure of the FA-S consumer function and Azure Cosmos DB data store. It shows the FA-S consumer function as a node connected to an Azure Cosmos DB data store, also as a node. The application map for the FA-S consumer function shows that there is a dependency between the FA-S consumer function and the Azure Cosmos DB data store. It also shows the FA-S consumer function is not dependent on the FA-S producer function nor the Azure Event Hub. A diagram shows the following flow: 1 instance 98. 6 MS239 calls NCAFAS busser Azure Cosmos DB. Figure 12. 42. This application map shows the FA-S consumer function as a node connected to an Azure Cosmos DB data store, also as a node. Used with permission from Microsoft.